Good morning, everyone. We're recording live. No homework today, but this is lecture 5, I believe, correct? All right. Why don't you give me a second and we'll play some tape.
Hello, space fans, and welcome to Professor Britain's Wack Universe.
Yeah. Okay. Good morning, space fans. I'm just getting the lights all set up here. It's been kind of a wild night, but I am here and I'm sleepy, but I'm ready to teach you guys everything I know about the forces of nature, gravity, and today we're going to start transitioning into atoms and light, which is a subject that I enjoy teaching and I hope you will enjoy learning. We should have a couple of things to talk to the class about before we get going. As you know from my email, I decided to cancel homework today because our homework that we were going to do for today is based on the lecture we're going to have for today. And sometimes that's okay, but I just felt like getting the lectures ahead of the homework because we, oops, sorry, I just lost you. Because we have an exam coming up, right? The look on your face, Will, just kind of says it all. Okay. The exam was supposed to be for Thursday. And as I mentioned briefly in that email, I was thinking we would move it all to Tuesday. That gives us one more day of lecture to prepare, to cover some material, and it just kind of pushes it off. Also, I have to imagine, the more I think about it, that if I were you guys and I were going to study, probably it would be easier to carve out the time to study on a Sunday than it would on a Wednesday. Is that a correct assumption or is that incorrect? I mean, you guys might work on. Sarah's saying, yeah, a little easier to study on a Sunday than a Wednesday. Evelyn?
Either is fine.
Okay. Will, Shay? We'll put it this way. Does anyone have any objections to putting it off until next Tuesday?
No, absolutely not.
Okay, cool. And Cameron says Sunday's better. Okay, all right. Jose says he's on board with this too. Yeah, kick that can. Now listen, in theory, when I used to teach this course in the summer, I would have a midterm exam and a final exam. But we have so few classes together and so much cool stuff to talk about. My thinking is that we'll just take one exam, the midterm exam, and that will be it. It will count for more. It'll count for half your grade, so it's worth hitting it hard. But I think we'd rather spend our last day together learning about more cool stuff in space than we would being stressed out taking an exam. I have to imagine that's how you guys would feel, right?
Yeah.
So honestly, whatever you get on the midterm will probably be close to what you get on the final anyways. They're usually within a few points of each other. So let's just go through that stress once, not twice. And mostly because I'd rather spend the time teaching you stuff, not testing you about the stuff I taught you. Does that make sense? I guess I'm just not into assessment. I believe that we should hang out and talk about science together, and then it's up to you to go out into your lives and use it for good or evil, as the case may be, okay? And to have fun with it and enjoy it. So I'm mostly concerned with fun. I like to entertain myself, and somehow that ends up entertaining you guys too, so that's good. If anyone has objections to that, I could, of course, give you your own personalized final exam. I'd be happy to do that. If there's any volunteers.
Yes, please.
Up on that, okay? But barring that opportunity, let's try to do right on the midterm, and that's why we're gonna, another reason to put it off until Tuesday. Okay, so let's see if any slideshows are up. Let's grab them. I'm a little bit sleepy today. I did not get a lot of sleep last night because it was pretty wild out here in downtown, and that's fine. But you're just going to have to bear with me if I'm a little more ums and ahs than usual, okay? You might get a few more of those. Now, I think last time we basically covered mechanics. We did Newton's version of Kepler's 3 laws, right? We learned about escape velocity, and then we did a lab on calculating the period of the International Space Station. By the way, how many of you got to see that rocket launch this Saturday? It was pretty cool, right? I missed the initial launch by a few minutes, but then I caught the whole rest of it, and I went back and watched the footage of the launch. And boy, I don't know what you guys thought about it, but that space capsule, the Dragon space capsule, looked pretty space age and high tech. It looked like something straight out of Stanley Kubrick's 2001. I was feeling it. What were you thinking, Joel?
I agree. It was pretty crazy. I have a question though.
Okay, hopefully I can answer it.
So, kilometers per second. You said they have to go 11
Yes.
kilometers per second.
Or 10. Did I tell you? I told you about the spin of Earth, right?
Well, yeah. They have to go 10, and then with the spin of Earth, it'll take them up to 11.
That's the basic.
Now, so in order to get kilometers an hour, you multiply that by 3,600, because 60 seconds in a minute, 60 minutes in an hour.
Yeah.
Right?
Yes, that sounds right. Yeah, per hour. So hours on top. No. Hold on. Let's do that carefully, Joel. So if you have kilometers per hour and you want to convert to kilometers per second, you need to divide by 3,600, correct? Can you see my
Right.
board?
I was just doing the conversion of what they have to be going.
Oh, okay, sure. All right. Okay.
So that comes out to 39,600
In what units?
kilometers per second.
No. No,
If
not at all.
if they have to go 11 kilometers, no.
Oh, I sorry. You're trying to go from kilometers per second to kilometers per hour. That's what was happening, right?
Yeah.
Sorry.
Yeah. So it'd be
let's say they have to go 10 kilometers per second because they'll get a little boost from Earth's rotation. Then you are correct. You would need 3,600 seconds per 1 hour, and that gives you
36,000.
yes.
So they were only going 27,700 before they blew the second pack off.
Okay, so there's a couple of issues. One of the reasons, all right, so I'm not much of a rocket scientist, to be honest. The engineering aspects of it are a little bit above my pay grade. But
Okay.
I will say this. You guys remember from calculating your escape velocity, right? That your escape velocity depends upon your radius. And I think we didn't have time for this problem, but it also depends upon your height above Earth, right?
Okay.
So one of the reasons probably for doing multiple stages, it wouldn't be hard to confirm this, but I'm just going off of instinct here, is that if the escape velocity goes as the square root of 2gm, and I said it was the radius, but what it really is, Joel, is it's really the radius effective, the effective radius. And that means it's the sum of the radius of Earth plus that height of the shuttle.
Uh-huh.
Do you see what I'm getting at here?
Yeah, so it's like the International Space Station math we did.
Right.
Yes.
With assuming that the distance is the radius plus the height. So think about this.
Yeah.
First of all, at the latitude of Cape Canaveral, I did a calculation once. It's not too hard, but I think the circumference of Earth divided by 24 hours, you're pretty close to Mach 1, right? You're above Mach 1. So it might actually be a little bit above 1 kilometer per second. The second thing is they don't just do one burn, they do multiple burns. And by doing burns at some height above the surface, at some altitude, your escape velocity is going to drop. because you're now adding the height of the shuttle into the radius of Earth. And that probably lowers the escape velocity a bit so that they can achieve it with a second burn at a slightly lower speed. Did that make sense? For instance,
Yeah.
it's 10 kilometers per second or so at the surface of Earth. But if we go up, you know, I don't know how it is, 80 kilometers, 90 kilometers, that might drop to 9.8 kilometers per second or 9.7. And that all might balance out around 27,000. Our numbers are close to their numbers, but there's going to be slight differences for the engineering of the multiple stage rockets. You know what I mean?
Okay.
And by the way, that's my intuition, my gut level intuition of what the answer is. It would be cool to ask a NASA engineer, because I'm sure there's a whole crap load of complexity underneath the surface. I mean, we're doing the babyest version, right? And it's still cool to do the baby versions, but there's a lot of science that goes into that stuff. But maybe during my tea break here, I'll look at it. But cool question. It wasn't quite 36,000. It was about 10,000 less than that. And Joe, I think your point is that's pretty significantly lower. And there's probably a couple of reasons. And I'm guessing my final answer is partly the spin of Earth at that latitude is a little more than 1 kilometer per second. And probably by making it multiple burns, you can get away with less because you keep firing from an effective Earth that's larger in radius. You know what I mean? One of the problems I did not have us do in the interest of time is I asked you guys to calculate the escape velocity of our solar system, but instead of starting from the sun, we start from Earth's orbit. And what happens is you basically effectively smear the gravity of the sun out over a sphere of 1 AU. And so it's possible to escape the solar system at lower speeds. And that's how the Voyager and the Pioneer spacecrafts were able to slingshot their way out of our solar system into deep interstellar space, where they travel to this very day. So, and by the way, let's turn this into one more teachable moment about escape velocity. Imagine that you had a planet and you kept its mass constant, but you doubled its radius. It would be a bigger planet, but it would still have the same amount of mass. In the case where the mass stays constant, but the radius gets bigger, the escape velocity would actually go down. And that's because you'd smear the gravity over a larger sphere, and the gravity tethering your rocket to Earth would be weaker. So that's almost counterintuitive the first time you think about it. You'd think that a bigger planet would always have to have more escape velocity. It's kind of true because they usually have more mass too. Jupiter is bigger, but it has 1,000 times, it has 11 times the radius, but it has 1,000 times the mass. For that reason, it's harder to leave the surface of Jupiter, the surface in quotes, of course, than it is from Earth. But if you simply just make something, if you spread the gravity out over a larger sphere, it becomes easier to escape. Okay, cool. Did we talk briefly about momentum and angular momentum? I think we did do that, right? Does anyone have something in their notes about that?
Wait, do what?
Do you guys have bits in your notes on momentum and angular momentum?
Yeah, I think so.
Did I show you the bicycle wheel?
Yes.
Okay, then we did that. So why don't we start today's lecture on energy? I think that would be a good place to go. Let's talk energy for a second. Like momentum, energy is an abstract concept. It's an abstract concept in physics that's not as easy to think about initially as, say, a velocity or an acceleration or a mass. But the payoff for learning to think in terms of energy is that you get a deep insight into how nature works. Energy is something we talk about all the time in our daily lives. I have a more energy efficient house. I've got a more energy efficient car. Aw, crap, I'm out of energy. But what the hell is this stuff energy anyways? Most people think about energy as like the blue glow that surrounds Superman, but there is a technical definition to energy. Unfortunately, the technical definition of energy is so subtle, so sublime, that you almost have to already understand energy before you can understand the fundamental definition of energy. Let's give it a shot so I can explain what I mean. Let me find a good marker here because my markers are all kind of Let's try this one. Nope, that was totally different. Okay. Try this one. Okay. So let's talk energy. Everyone seeing the board okay here? Oh, someone's got a little bit of TV noise in the background. Might be you, Joel.
Oh, no, it's me. Sorry, I didn't realize my mute was off.
That's okay. Oh, well, yeah, just
It's my cartoons. Yeah,
Oh, yeah.
I'm muting.
I understand. You got kids in the house. You need the tunes. And adults. Okay. So here's the deal with energy, okay? The fundamental, the real definition of energy is it's a force multiplied through a distance. And while that is strictly true, it's not helpful. Not at your stage of development, okay? Here's some things that I can tell you about energy that will be more helpful to you. Energy, here's the first thing that we say about it. Energy is in physics a conserved quantity. And you've probably heard of the conservation of energy before. In physics, things that are conserved are called conserved quantities. And that means the total energy of a system is always constant. What is the use in knowing that? It gives you Nostradamus-like powers at determining how a system will evolve with time. You can literally predict the future by knowing things like this. Momentum is also a conserved quantity. And this is why when things collide with each other, we know how they're going to ricochet off each other, knowing that momentum is a conserved quantity. So the total energy in a box is always constant. And if you start with that principle, you can then deduce what is going to happen when a system evolves. If you heat it up, if you cool it down, in other senses like that. Hold on, guys. I'm working on my blinds here. It's just a little bit of glare. Okay. Here's
Hey, Brandon,
Yeah?
is constant energy the same as potential energy?
So that's my next thing to address, Shay, is that energy takes various forms. So let's make this bullet point 1, energy is a conserved quantity. And the second thing is that energy takes various forms. One of the things that's cool about energy is it's very abstract and it can transmute itself like a shape-shifting ghost from one type of configuration to the other. Now, there's sort of top-down classes of what types of forms energy can take. And one of them is, as Shay said, potential energies. Potential energies are energies stored in a force field. I'll explain that later. Potential energy is energy stored ultimately in some kind of a force field. But if that sounds a little too Star Trek for your taste, you might just think of it as storing energy, like in a battery, okay? A battery holds potential energy. A spring holds potential energy. There's even gravitational potential energy, which I'll start with. Other forms that kinetic energies can take are called kinetic energies. And kinetic energies are usually stored with motion. It's kind of like the energy of motion. Heat is a form of energy, okay? Although ultimately heat is sort of connected to kinetic energy. And I should also mention light. Light is another pure form of energy, which is sort of potential because it involves a field, but it also travels in motion, so it's sort of kinetic. Light is almost like its own thing. Light, in fact, I'll take the bullet point away from heat. I'll put heat as a subset of kinetic energy, but light is actually kind of like its own beast. So I'd say the 3 main forms you find energy in nature are potential energies, kinetic energies, and light. Now, I still haven't really helped you understand energy that much yet, but I'm at least giving you the first pass, the top-down view of what's going on. So Shay, potential energy is just one form. We're going to start by learning about a specific type of energy, because sometimes learning about a specific thing helps you understand it better. Is everyone okay if I erase this? I know I just wrote it down. All right. No objections, right? Okay, so here we go. Let's learn about potential energy. Okay. So this is the type of energy called gravitational potential energy. And it's a relatively simple form of energy to begin learning about. So I think it's as good a place as any. Excuse me. So here's the setup for gravitational potential energy. Let's do it in real life and take a picture. So here is a 1 kilogram mass. It's a test mass. And at the beginning of my episode, it will be down on the ground, down here at my feet. And I ate some potatoes and eggs this morning. So I've got muscle energy. Okay, there's energy in my muscles because I stole it from the potatoes. And now what I'm going to do is I'm going to use that potato muscle energy to lift this 1 kilogram mass 2 meters off the ground. And you know it's 2 meters because well, in a classroom I would show you, but I guess you're just going to have to trust me. Here's my 2 meters, 1, 2, and I'm going to lift it up over my head. And here we go. Well, here we go. I'm holding, oh shoot. These damn cameras don't have the field of view I need. It's not like teaching in a classroom. Okay, so here's my 1 kilogram mass, 2 meters above the ground. And I'm basically storing some potential energy up here. Let's take a closer look at it. I've got too many things in my hands. So here I'm holding my thumb, and this 1 kilogram mass is suspended over my head. I'm in danger of dropping this on my head and having an unfortunate accident right here on the camera, or I'm about to give myself a concussion. I can feel gravity trying to rip this thing out of my thumb. And that means that I've done violence against gravity, right? I've forced this against the will of gravity. If it was up to gravity, gravity would slurp it back down and stick it to the ground. But I've said, oh, hell no, gravity, not today. I'm fighting you. I'm pushing up, and I'm storing something in your potential energy field. I've actually inadvertently made gravity kind of like my servant or my minion. He's like a genie trapped in a bottle. Because gravity wants to rip this down to the ground so much, I could do something with it. I could take it over to a small village and I could release this 1 kilogram mass on some unsuspecting villagers, and gravity would punish them from the sky. Anything is possible. Or I could power a water mill. I could do anything with this one test mass of potential energy. Let's draw that setup, because this type of energy is gravitational potential energy. It's the energy stored in a gravity field when you've made gravity your genie who has to do your bidding. So let's define this as energy stored, like all potential energies, but this time in a gravitational field. And let's draw the picture. We had the ground, we had a 1 kilogram mass, okay? Let's just write the mass as M, because it doesn't have to be 1 kilogram. It just happened to be 1 kilogram in my particular situation. The height above the ground we'll call little h, because physicists like to do that. And we define the potential energy, PE, as the product of mass times little g, the local gravitational acceleration, times the height above the ground, which I've lifted it. So Mass General Hospital, that's the abbreviation. Class, can you remind me about G again, little g? Sorry. We learned about little g in our lectures Thursday. What did you learn about it?
Is it the 9.8 meters per second squared?
Sure. Or how about 9.81? Or how about 9.808? I don't know. There's several sig figs, Evelyn. How many do you think we need? It's up to you.
2.
How about 1? Well, 2 is fine, but you know what's even cuter? It's cuter to do 1 because then you really don't give an F and you're a badass. You know what I mean? And you can kind of get the same results too. But let's just take a look at the local acceleration of gravity in Earth. Actually depends upon where you are on Earth after a few sig figs. The value of G. I don't know at which significant figure it starts to affect. Oh, these people are only doing 2 sig figs. Oh, wow, look at this. 9.80665 meters per second squared. How about that, Evelyn? Or how about just 10?
Too many sig figs.
Yeah, too many sig figs. I think, so if you take a physics class, which you may have done, Evelyn, I remember my physics classes, they usually use 3 sig figs, 9.81. Physicists are a little sloppier than chemists, and astronomers are way sloppier than physicists. We're we're becoming a higher precision science. We would like to be high precision, but sometimes it's also cool to just kind of know, how far away is that star to within a light year, you know? So anyways, or maybe it's just my personal nature, Evelyn. Maybe I am just a low precision kind of guy, you know? That's probably what it is. So I'm gonna just call G for fun and giggles 10 meters per second squared. Remember, it's the local acceleration of Earth's gravity. It also makes the units nice and simple. Why don't we calculate together, Evelyn and friends? Let's calculate the sample problem that I just did, okay? So I have a 1 kilogram mass, and I've suspended it 2 meters off the ground. And the purpose of this sample exercise is going to be for us to figure out the units of energy together. So the potential energy, mgh, would be 1 kilogram. Let's do the units in shocking red, okay? So one kilogram, that's going to be multiplied by the local acceleration of Earth's gravity, 10 meters per second squared. And that's going to be multiplied by the 2 meters I've lifted it off the ground. Now I'll do all the tough stuff. 1 times 10 times 2 gives us 20. Evelyn, can you tell us the units there by smushing them all together?
Kilograms times meters squared.
Meters squared, because that's a meter on top and that's a meter on top.
Divided by seconds squared.
Excellent. Let's say that one more time together. It's a kilogram meter squared per second squared. Kind of a mouthful, wouldn't you say? Huh. So that's what energy is. This whole time I've been wondering about energy, and now I know energy are kilogram meters squared per second squared. Now, I'm not sure I understand what that means. See, I understand what a kilogram is. A kilogram is something that I don't want dropped on my head. And I understand that a meter is like half my body, and a second is like, pip, pip, pip. I waste those all day long, right? But meters per second, I kind of understand. That's kind of like how fast I'm going. And meters per second is like how fast I'm gonna be going if I keep going. But once you get to kilogram meters squared per second squared, your brain just kind of does I don't get that anymore. I don't understand. And that's when it's a good time to hide your confusion, to sweep your confusion dust bunnies under the rug and invent a new unit of energy that will make it feel like you know what you're talking about. And that unit is called the joule. This is also defined as 20 joules of energy. Or just simply put, 20 capital J. So let's add one more note to our tidbits about energy. Actually, let's do a whole tidbit on the units of energy. Let's make sure you guys have that. I'm going to erase the top. Units of energy. Okay, so we have in the MKS system 1 joule, which is defined as 1 kilogram times meters squared per second squared. This is our standard MKS unit of energy. Do you guys know about any other units of energy? Because it's kind of an interesting thing to discuss.
Kilowatt.
Sorry, Joel, can you say that one more time?
Kilowatt.
Believe it or not, Joel, kilowatts are a unit of power, and power is a slightly different thing. Today's lesson is going to include a lecture on power, so we'll come back to that. One of the reasons you might have confused kilowatts with energy is because when you pay your electric bill, Joel, you pay for not kilowatts, but kilowatts times hours. So when I pay my electric bill from National Grid, and I'm shamefully looking through the details in that long list of scams that they perpetrate on you to charge you. The unit comes out to be a kilowatt times an hour. But because a times an hour is an awkward thing to say, people forget that it's kilowatts times hours. So kilowatts would not be energy, and that's an important thing I want to discuss. Hey, Joe, how about your gas bill? Have you ever noticed what you're paying for there? The unit they use in gas, anyone know?
I forgot.
It's also similar to what they use to rate air conditioners and other heating systems. Now,
BTUs.
BTUs.
Which stands for British Thermal Units. Now, if you actually look at your national gas bill, they nickname them therms. I think they call them therms, but I believe that stands for BTUs, and BTUs stands for British Thermal Unit. In this, astronomers use something called ergs. There's an energy called an erg, which is 1 gram times a centimeter squared per second squared. Ergs are pretty esoteric, so you won't see them in this class, but if any of you go on to study more advanced science, you may come across ergs in your future happenings. Some others we should talk about. How about in the imperials? Wait, can I erase this, guys? Down here? Yeah. How about the imperial units of energy? This is one that you ought to know. As the US uses the imperial system of units. While you think about it, I'm going to twist the blinds one more time. I think this gives me slightly less glare today. Each day it's different. Oh, there's still glare. Okay, whatever. Any imperial units of energy, go. Thoughts? Deep thoughts?
I want to say thrust, but I don't think that's right.
No. Thrust is actually force. When you apply a thrust, it's a force measured in newtons. So
is like torque and tension, right?
Torque is force in a rotational sense. Tension is also a force. Tension is a force. But torque has the same relationship to force that angular momentum has to momentum. Believe it or not, I think I actually have a slide on torque. Do I have a slide on torque? That would be kind of cool. You guys know that forces are vectors. They have direction, and a force is a mass times an acceleration. But do I have an example of torque here somewhere? I guess this might be my best example of torque. It's not great, but if you have a force like this mass times this little g, and you apply it across a moment arm, it's actually kind of funny here that this is a real human arm, because they call the radius that you apply the force through the moment arm. So that's kind of cute. And a torque applies a force in a rotational sense. So for instance, when you push against a door, Shay, you're applying a torque because the radius of the door is fixed and you're causing it to rotate. So you're pushing along a rotational axis rather than on a linear axis. I thought you guys might have heard of calories before. Ain't you heard of calories?
No,
The
never heard of her.
Yeah, I ain't heard of those either. Oh boy. All right. So, anyways, the calorie, however, is not the calorie that you think it is. The British unit, the imperial unit, the lowercase calorie, is only 4.2 joules. But the food calories that you eat are actually kilocalories. And a kilocalorie, of course, is 1,000 calories. But here's what's weird. The FDA, in their infinite wisdom, decided that we should not print our food labels with the term kilocalories. Perhaps because we might end up sounding too much like our snobby European friends, you know? So instead of calling kilocalories, they actually just rename them calories with a capital C, which is even more fucked up because it leads to hideous confusion between the British unit calorie and then the American unit calorie for food. So food calories are a capital calorie. Pretty messed up, huh? Okay, let's look at some examples of
Now I understand my dog's food label.
Oh, really? Does it say kilocalories?
Yeah.
Oh,
It
wow.
says K calories.
So does mine,
And
you're right.
And I never understood. I thought it was stupid.
No, they're actually labeling it right for your dog, and they're labeling it wrong for us. I think it's the American Sugar Association trying to trick us into eating more candy bars. Speaking of which,
Keep us fat.
my girlfriend, I like these granola bars from Trader Joe's. They're like peanuts with little drizzled chocolate, and I just love them. You know, I eat them in the morning, I eat them in the afternoon. And one day she went, you know, Brendan, that's basically a candy bar. And I said, no, it's a granola bar. She said, it's a candy bar. So let's find one of these things and let's check out the number of calories. Hold on a second. In fact, I think I'm going to have one right now because I'm kind of hungry. I'm going to have one right now. I like these sweet and salty Cascadian Farms. I also like the nutty bars from Trader Joe's. I really like these ones. This is the nuts and sea salt. And according to this, 200 calories. I guess that's a little less. I think a Snickers bar usually has about 230 calories or so. So she's not wrong. It's basically a candy bar in terms of calories. Oh, these ones, the Cascadian Farms, are only 170. So let's say that the professor eats a candy bar. Let's keep all this handy here, okay? And let's do a little sample problem with units of energy together. Let's say that a professor, if you will call him that, eats a 200 capital calorie, quote unquote, candy bar. It's too bad she's not here because she would be laughing in the corner right now. A candy bar, and let's say that the professor started to feel guilty about that. Maybe someone in his life made him feel guilty about eating this thing. So he decided that it was time to hit the gym and do some exercise. But of course, he's a wimpy physicist, right? He's a wimpy astronomer, and he needs an exercise appropriate for a wimpy astronomer. So introducing the 1 kilogram squat, an exercise appropriate for wimpy astronomers, okay? You put it down on the ground, you lift it up, you go, you pick it up 2 meters over your head, okay? And then you just keep doing that until you've worked off your candy bar. Now, if you invent a new unit of exercise and you call it the 1 kilogram squat, how many joules of energy does a 1 kilogram squat burn from our previous calculations? We know this because we just calculated it. Just look at your notes.
20.
Oh, say that.
20 joules.
Excellent. Was that you, Evelyn?
Yeah.
20 joules. Nicely done. Okay. So here's the question.
Wow.
How many kilogram squats do I have to do to work off the candy bar? Assuming that a 1 kilogram squat will burn 20 joules. How are we going to do that problem? Evelyn, since you were sort of on the ball, we could pick on you for starters. I always like to pick on you, Evelyn, because you're an easy target, okay? How would I
Great.
begin this? Would you know how to start that?
You just multiply, or no, you'd,
Could I just interject and make a recommendation? Probably whatever you're saying is about to be good and true. But could we do it with dimensional analysis for style points?
sure.
Okay, so what's our first step?
You put down what you're converting
With its units.
with its units.
So what are we converting here?
Converting calories to joules,
How many?
200 calories.
In fact, I'd like to suggest to you, Evelyn, that we're not just converting to joules, we're converting to a new unit of energy called kilogram squats. Because I kind of just invented a kilogram squat. In fact, I'm going to use the triple equal sign to let you know that I invented this exercise, okay? Kilogram squat is a unit of energy because you can convert squats into joules. Do you follow my logic?
Yeah.
This is what's cool about energy. Energy can flow into different forms. One moment, it's a bloody candy bar, right? One moment, it's a candy bar. The next moment, it's joules, and then it's exercise. Okay, so what am I going to write down, Evelyn?
200 calories.
Good. And that's capital calories, right?
Yes.
Okay, now what?
You multiply by a division bar.
Okay, and what are we going to do for units?
Put one calorie on the bottom
Okay.
and 4.2 joules on top.
You've been tricked by the FDA. These are not actual calories. These are kilocalories, aren't they?
Right. Okay.
So let's add the K in front. Why don't we convert from kilocalories to calories? What's the conversion going to be?
1 kcal is 1,000 calories.
Okay, now we'll do our next division bar and put little calories in the bottom. And you said the conversion was what to joules?
1 calorie is 4.2 joules.
Nice. And lastly, we're going to convert to what?
Joules.
No, we have joules because we've canceled out kilocalories and we've canceled out calories. Joules remain. But I'm suggesting to you we can go one step further.
Oh, kilograms per squat?
Not per squat. Per means it's on the bottom. Kilograms squats is kilograms times squats. I just made it up, okay? So I'll put kilograms squats on top, and I will put joules on the bottom. And what's my conversion factor?
20 joules is 1 kilogram times squat.
All right, so 20 goes on the bottom, right?
Yeah.
I should have asked you that. I hope you would have known that. Guys, never forget, dimensional analysis is always trickier than you think it is. It's very easy to make a mistake where you put the wrong number in the wrong position. It's easier than you think. Okay, punch them up. Oh, by the way, how many of you have the Casio today? Who's my friend and who's my enemy? All right, I'm seeing 2, 3, Sarah, Will. Yeah, woo, ding, ding, ding. Now, I don't know what's happening. Jose, I lost you. You're hiding on me. And Cameron and Alba, I hope you've got one too. But when Jose comes back, we'll ask him what's up. You guys do me proud. Okay, so do 200 times 1,000 times 4.2 divided by 20.
42,000.
Holy jumping Jesus. I'm going to have to do 42,000 kilogram squats. Do you guys think I can do 42,000 kilogram squats?
No.
I don't think I can. I mean, I don't know if I could. I don't even know if I could do this 100 times without getting tired. That's how jumping jacks work, right? After all, there's a lot more than 1 kilogram tucked under this beer gut, let me tell you, okay? How many, suppose I did 1 squat per second. How it would take me 42,000 seconds, right? How many minutes, how many hours is that? Where's my calculator? How many hours is it? Do it without my help. You understand what I'm saying, right? If I do 1 kilogram squat per second, it's going to take me 42,000 seconds. How many hours is that?
Almost 12 hours.
Yeah. I'd be squatting for 12 hours straight, wouldn't I? You've had the Casio since the first day, Alba, and ye shall be remembered in the halls of Calculator Valhalla for your bravery and your wisdom. Okay, so, and I'm very glad about that, though, I really am. Think about it, guys. 12 hours of 1 second kilogram squats. That would be a... No wonder why I shouldn't eat these things, right? This is why I'm losing the battle at 42. The battle of the waistline. In any case, probably shouldn't eat those. Let me tell you about a more abstract unit of energy, one that you've probably never seen before, but you're going to see today. It's useful when we deal with the quantum world of microscopic atoms, and it's known as an electron volt. Now, it is not the same as a volt. A volt is a unit of electrostatic potential, whatever that means. But there's a funky unit of energy called 1 electron volt. And you can think of the electron volt as basically a teensy tiny packet of energy. And we use electron volts when we work with atoms, which we are going to be doing today. 1 eV, as it's called, lowercase e, capital V, is 1.6 times 10 to the negative 19 or 16. How come I can't remember this? Negative 16 joules. Or is it negative 19? I am sorry to report that in my sleep-deprived brain, I have forgotten whether it's 10 to the minus 16 or 10 to the minus 19. That is so awful of me. Let's just type 1 eV to joules. Oh, it's 10 to the minus 19. Sorry, guys. 1 electron volts is 1.6 times 10 to the minus 19. Please forgive.
There's only 3 zeros. It's
Yeah,
1,000.
there's no big deal.
No big deal.
That's a lack of sleep talking there. You know, all this talk about candy bars. Well, actually, first of all, let's talk about a different form that energy can take. And if you guys are seeing my screen right now, I'd like to teach you a little bit about kinetic energy. Not too much, just a little bit. Here's a legendary picture taken by the MIT physicist Doc Edgerton. He's the one that did the milk drop experiments. And he took this lovely, beautiful photo of a bullet rupturing a apple. And it's a wonderful demonstration of kinetic energy. Kinetic energy is the energy associated with moving things. One way to think about energy is a bullet does not travel at whatever 320 meters per second from the get-go. It starts off in a banana clip just sitting there at rest. And something has to accelerate it and push it forward to travel at the speed of sound. And that's going to cost energy. You could define kinetic energy as the energy that it takes to accelerate a bullet or a particle of some mass up to some speed. Another way to put it is it's just the energy of moving things. So sometimes I say that kinetic energy is just the energy associated with a moving object. That's probably not the best definition, but it's going to have to do. It's the energy that makes things move, okay? And it has a simple formula of 1/2 mv squared. Maybe we can figure out how much kinetic energy. Is Joel still with us?
Yeah.
Joel, from your time in the, I don't know which branch of the service you were in, Army. Do you know, like, give me, I want to look up a standard bullet. I want to know its mass and its velocity. And I've tried to do this before and I've gotten a variety of different results, but I thought you might be aware of some kind of interesting bullet. We could look up its mass and its velocity and try to calculate its kinetic energy to get a sense of how much kinetic energy a bullet has. So I don't know, maybe a rifle, it could be you know, one of an AR-15, or it could be anything, whatever your choice. Can you give me a standard grain or a bullet, like a 5.56 or whatever it would be?
You can do the 5.56 or the 50 cal, which is 0.50 cal.
0.50 cal.
Yeah, 50 cals.
50 cal bullet. And let's look up its mass first, and then we'll look up its velocity. So I think this should be something that's pretty easy to Google, because they're going to have a standard mass, right?
Yep.
So this says about 23 grams, okay? So let's start by writing this down. A 0.5 cal sniper bullet is here. So it's a 0.5 caliber. That's right. Shay, you were in the service as well, so you might be familiar with this. 0.5 caliber bullet has a mass of, did they say 23 grams? That's less than I would have thought. I would have thought it had more mass than that.
Yeah, 50 cal should have more than that, I'm thinking.
But 23 grams, you know, we'll just take them. We'll assume they're correct for now, because I have no reason not to. But
what does that translate to ounces?
At this point, I have a harder time thinking.
Roughly.
Let's just type it into Googie real quick, so I don't do anything stupid. Hold on. Let's keep that up. I'm fighting all these different pop-ups here. 23 grams. Do you know how many ounces it should be?
No.
Almost an ounce.
No, I have a 50 cal shell. Let me go get it.
Really? Do you have do you have something to weigh its mass on, or its weight?
Wait, the whole cartridge is 23 grams? Bull.
I don't know. Tell me.
It might have 23. Might have 23 grams of powder.
Okay.
But that round that comes out. That's got to be. Scroll down. It had dimension stuff on the right.
Oh, they have its velocity too, which is what I wanted.
Yeah. Yeah, it goes 2,700 feet per second.
27.
Yeah, the bullet mass is 42 grams.
Okay, so we're going to use 42 grams and 923 meters per second, okay? Let's go with 42 grams, 920 meters per second, okay? 42 grams, 920 meters per second. That works. 42 grams and a velocity of 920 meters per second. I guess, can I tell you what I'm thinking, guys? I think this is an interesting problem, because I want to know how the energy that it takes to accelerate that bullet compares to the energy of me lifting up a 1 kilogram squat, just so I can have some sense of it in my mind. So let's calculate its kinetic energy. Let's do, oh, I'm sorry, we have to convert some things here. Kinetic energies, potential energies are always MKS units. So what do we have to convert the grams to?
Kilograms.
Okay, what's the conversion from grams to kilograms? Someone's got to know.
1 kilogram equals 1,000 grams.
So where does the 1,000 go?
On the bottom.
Good. Okay, I'm just testing. So that's sliding it back 1, 2, 3, 0. So that's 0.042 kilograms. And we already have meters per second, so we're good there. So let's calculate our kinetic energy. It's 1/2 times 0.042 kilograms times 920 meters per second square thereof. Can you guys punch that in for me? Don't forget to hit equals after you square. Just shout it out when you get something for me.
Yeah, sorry, I was wrong, huh?
What were you right about, Shay?
Everything.
Oh. It's okay to be wrong as long as we figure it out. I guess it's okay to be wrong unless you're taking a test. Then it's definitely bad to be wrong. Joel, can you read that to me? I'm having a hard time seeing it through the little window.
17,774.
Oh, okay. Well, round it to something tasteful, you know? 2 sig figs.
18,000.
And the units? It's an energy.
It's not joules.
Why isn't it joules?
Oh, no, wait. It is joules.
Yeah, it's MKS energy. It's kilogram meters squared per second squared.
Yeah, because meters squared meters per second got squared. So that's
That's
M
right.
squared over S squared. Yeah.
Very good. Now you're starting to be good at unit balancing. So that's 18 kilojoules, or 18,000 joules. That's pretty wild. That's a lot more than my 20 joules to lift up that 1 kilogram weight. I guess that's what makes bullets so destructive, right? You don't want to be on the other end of those. Okay, cool.
And ironically, Evelyn's eating an apple.
Oh, really? Right now?
Yeah.
All right, I'm going to eat an apple too. That'd be good for my health. I have a bunch over there on the shelf. In fact, all this talk about apples and candy bars is getting me kind of hungry, and it gets me thinking about other types of energy. It gets me thinking about, what temperature do you guys cook a turkey at on Thanksgiving Day? Let's talk about that.
I have no idea.
None of you have ever cooked a turkey before?
Yeah, it depends how late I'm running.
Call yourself Americans. What about a roasted chicken?
165 or 65 degrees Fahrenheit.
What?
That's a
Whoa.
slow cooking bird, right?
That is.
350?
I guess.
Yeah.
maybe.
You can go
Oh,
to like
what temperature do we cook it at? Oh, I
Not the temperature of the meat, but what do you set your oven to? You set it to 350 degrees in what unit system again, Evelyn?
Fahrenheit.
Yeah, Fahrenheit. So let's say we all get together and we roast a turkey one day. You know, just a couple of fellas cooking a turkey. And we decide that we need a little bit extra, so we're going to get a pot of boiling water. And what we're going to do is we're going to make some boiled turkey to go with it. But what temperature do I boil the water at in the Fahrenheit system if I'm boiling some water?
212.
Very good. Water boils at 212 degrees Fahrenheit. So I got one turkey that's cooking in the oven at 350 degrees Fahrenheit. And then I've got myself a turkey that's in boiled water here. And that's 212 degrees Fahrenheit. And suddenly I realized, ding, the turkey's done, and I don't have my oven mitts. Now, that means one of us is going to have to put their bare hand into the 350-degree oven real quick to pull out the turkey. And the other person is going to have to put their bare hand real quick into the 212-degree vat of boiling water to pull out the turkey. So which job would you prefer? Would you rather put your hand in a 350-degree oven or a 212-degree vat of boiling water?
I'd rather just go home.
But the problem is you need the turkey. Jose, if you go home, you don't get to eat any turkey, and that's unacceptable because we're so hungry. We got to do something. You got to put your hand in the oven real quick, or you got to put your hand in the water real quick. What's it better to do?
in the oven because that's only air temperature.
I don't know, Joel.
Water.
You're going to burn yourself. Isn't the temperature higher there? That seems like it's going to be worse than the vat of water.
Yes,
Air
but it's just. Go ahead, Evelyn.
Air is a weaker conductor of like thermal energy.
Oh, okay. All right. So you're using some fancy terms. A conductor, you say. A thermal conductor. But wait. So say that again. Air is a better or worse thermal conductor? What did you say?
A worse thermal conductor.
Fine. But what do I care about that if the temperature is higher? So explain the microscopic bits there. Shouldn't I be worried that the temperature is higher?
Even though the temperature is higher, it's like you would feel it less because the particles aren't as dense as the water.
So you're saying I don't feel temperature, I feel particle denseness?
You feel the difference in temperature.
Something like that. Yeah. This
Something
is Evelyn pretty much has it right. I'm not gonna quibble too much. That was a pretty decent description if you ask me. And here's the picture that Evelyn maybe has in her mind here of a solid versus a liquid versus a gas. She's saying that the particles are much more dense inside the liquid than they are in the gas. But okay, so Evelyn, help me flush this out then to make sure that I understand it. Why does the denser particles end up hurting me more?
You come in contact with more of them?
But your hand is surrounded by air particles. You come in contact with them, okay.
They have more kinetic energy?
They actually have less kinetic energy, believe it or not, Evelyn. The particles in the liquid per particle has less kinetic energy than the particles in the gas. So let me see if I can just clean us up a little bit here, although you did a very fine job. Very, very satisfied. The thing that I've been doing with you guys here is a little exercise, a fun exercise, in the difference between temperature versus heat. Although when you said thermal energy, that could be a corollary for heat, so I'm okay with that. But let's talk about temperature versus heat. The particles in the water actually have a lower temperature, and therefore they have lower kinetic energies. But they contain more heat because there's more of them to transfer. I guess one simple way to look at it would be, would you rather get hit by 1,000 BBs or 150 caliber bullet? Actually, neither of those sound particularly good. But I wonder if 1,000 BBs might hurt you worse than a single 50 caliber bullet. That's kind of a tough thing to know because a 50 caliber bullet can kind of kill you, and that's no fun either.
Well, the BBs would probably be going. Well, they do go slower, coming up like a shotgun. A shotgun doesn't have one round; it has like it's two
bunch of
BBs
pellets
out of the shell.
But there's so many of them, right?
Right, but they're going at a much lower velocity. So the force that they hit you with, and the size of them, is much less. And they wouldn't all necessarily hit you at the same time.
True.
And they don't all hit you in the chest. Might hit you all over your body. So it's like 1,000 bee stings, right, compared to Mike Tyson punching you in the face.
Right. Yeah. And that's kind of the same with what's happening between the. Yes. I like these analogies are weird, but I like weird. So let's try to, now that we understand it, because those analogies are kind of good, let's kind of use the definitions here of each of these things so that we can really polish our answer here. So heat properly defined heat is a form of energy. It's a transfer of energy. And it's a transfer of energy from point A to point B, which could be anything. Point A could be the air in the oven, and point B could be the turkey. Point A could be some Coca-Cola, and point B could be some ice cubes. If energy flows from Coca-Cola into the ice cube to cool down your Coca-Cola. Now, in nature, there are only 3 modes of energy transport, or 3 modes of what we sometimes call heat transport, because heat is basically energy. It's measured in joules, just like energy is. And does anyone remember the 3 modes of transport? Like, for instance, Shay or Laura from my Astronomy 1020 class, when we learned the 3 modes of heat transport? I don't know. So that's kind of like a general science thing that people should know about. Like, you know how it's kind of good to know that the Earth goes around the sun and that like stuff is made out of atoms, just some basic shit to get you through life. It's also good to know your 3 modes of energy transport.
Conduction.
Conduction is one of them. Let's write them down. Conduction, what else?
Convection.
Convection is another one. And what's the third one?
Come on, Shay.
Come on, Shay.
Damn it.
What?
I don't think it's a damn it.
It's not a damn it.
I also got extremely intoxicated last night. So.
Okay. Well, there was a lot of madness going on in the streets, so I couldn't forgive anyone for having a drink, I suppose. Not even myself. Or I could forgive anyone, I suppose. Anyways, what if we went outside and like it was sunny out and we felt some beams of sunlight tickling our nose?
Absorption?
No.
Transfer?
That is absorption, but the transfer mechanism is radiation, guys.
Damn it.
That's what we're here to study today.
And there's only one thing that's called a damn it, Shay.
What is it?
When the back of your rank or any pin falls off and it hits you in the head. Damn it!
I just thought it was my mental state today. That was the day.
No, that would be Confucius.
Confucius. One day I saw these two kids walking down the hallway in CCRI, and one kid says to the other kid, you know, they say in China, in ancient China, that the nail that sticks up gets hammered. And the other guy looks at him and goes, what's wrong with that? I get hammered all the time.
That's good.
Okay, so anyways, heat is a pure form of energy. So there is certainly more heat in the water than there is in the air. But that's not the same thing as temperature. And let's investigate temperature together. So does everyone have this down? Because I consider this important for your general well-being. Let's tackle temperature next. Temperature, properly defined, is the average kinetic energy of a system of particles. Those particles could be in a gas or a liquid or a solid phase. They could be in a plasma phase. Hell, they could even be a Bose-Einstein condensate if you wanted to get really crazy. There are more than 3 phases of matter out there, kids. Gas, liquid, and solid are just the most common ones. In our class, we're going to study plasmas. I don't know if we're going to mess around with Bose-Einstein condensates, but they're cool too. Now, it may be that not everyone understands the phrase average kinetic energy of a system of particles. So allow me to take a peek inside your everyday oven and model it with a little animation for an ideal gas that I have here. Pardon me. So let's tiptoe down. Let's tiptoe down to my ideal gas law. This is a classic from science. You guys can see here there's a number of, the air in the room that you breathe is composed of a mixture of 77% nitrogen and 21% oxygen molecules. So you can think of the little blue pellets as nitrogen molecules and the little red pellets as oxygen molecules. And they're all kind of bouncing around in free space together. And you'll notice that as the particles collide and smash into each other, they obey the same logic that bumper cars do or balls in a lottery box. They kind of travel in a straight line until they collide with one of their neighbors. They transfer energy and momentum, and then some of them slow down, some of them speed up. Even if you follow a single red particle of oxygen, you'll notice that its velocity is constantly changing. For this reason, it doesn't actually make sense to try to discuss the kinetic energy of one particle, because the kinetic energy of a single particle is constantly changing, and there's a lot of them. But if you consider what we call the ensemble of particles, the collection of particles, we know that energy and momentum must be conserved in this box, so that for every one little red atom that slows down, another blue or red atom has to speed up and take some of its momentum and energy. Therefore, the average, if you could imagine adding up all the kinetic energies in a microsecond and you could take their average, that average should stay constant. And this is what we mean by temperature. It's the kinetic energy of all the particles. Now, because kinetic energy is 1/2 mv squared, the velocities can easily change, but the masses of the particles usually stay fixed. So even though this is the proper definition of temperature, I'm going to give you a new definition of temperature that is basically a useful lie. And I'm going to tell you that temperature is kind of like the speed of the particles. That's not strictly true. It's not just the speed. But if you think about it that way, 9 times out of 10, it's going to give you good intuition. These things are all related by the ideal gas law, but I'm going to cover that when we do our lecture on the sun, because I've got a million other fun things I want to do today. Let's go back one more time to our turkey versus our vat of water. So Evelyn, just to be clear, in which situation here are the particles traveling faster? In the oven or in the water?
In the oven.
Correct. But they don't burn you as bad because
The D word, Evelyn. You said it.
or how about the H word?
The heat is lower average.
There's a lower transfer of heat to your hands. This is why you have to cook your Thanksgiving turkey bird for such a long time in your conduction oven, because it takes hours and hours for that heat to transfer into it. Another way to look at it, Evelyn, is that these particles are kind of like little bullets striking your hand. And when you're inside, let's, can I get this going again? Oops.
So if we had a convection oven, it would be somewhere in between boiling it and
no, because
doing
you're still using air, but convection ovens do work a little bit faster because they blow big hot bursts of air around. So they
Right.
can kind of superheat things a bit, like in an industrial kitchen. But they're never going to compare to the density of water. Really, Evelyn said it right when she talked about the density and the thermal energy conduct. What you are conducting is heat, and you can conduct heat more effectively through water than you can through air, because there's more bullets striking your hand per unit time in the water than there are in the air. So basically, Evelyn, you kind of said it perfectly. I really shouldn't have quibbled with it. I just wanted us to talk about the big H word, which is heat. See, the thing is, people sometimes use heat and temperature somewhat interchangeably, but they're not the same. One place where it's really going to strike us as important, when you go to outer space, things can get kind of weird. There's an outer layer of the sun called the corona, which is a high temperature plasma. And the corona can get up to 1,000,000 degrees Kelvin, extremely high temperature. But you could wave your hands through the corona without getting burned, because the corona has such a low density, even compared to the air in this room, that there just wouldn't be enough particles hitting your hand to transfer heat. So sometimes things can be really hot in outer space, but you would feel cold if you were foolish enough to try to get outside of your spacesuit and play around in it. You see what I'm saying? We have an experience of temperature which is kind of like heat. And so the things can get a bit muddled at times. Of course, we're going to need some temperature scales if we're going to measure things. And there are 3 basic temperature scales. I think we should try to take this down. Oh my gosh. Pardon me, guys. The rioting all night kept me up from sleeping, so I'm a little sleepier than usual. You can see here our 3 temperature scales that we're going to be using: the Fahrenheit, the Celsius, and the Kelvin. Why don't we go ahead and make a little chart in our notes? And this is a chart that I think helps students in the future if we have to convert in our minds. Can I erase this stuff? This will take us a minute, but I think it's worth it for your notebooks. And these are our 3 temperature scales. So let's grab a ruler and let's deal with some different thermometric substances. I'm going to have a column for the substance. I'm going to have a column for Fahrenheit, a column for Celsius, and a column for Kelvin. Okay, so this will be degrees Fahrenheit, degrees Celsius, and for some of you, introducing the Kelvin system of temperature units. Kelvins do not use degrees, they just use a K symbol. So we studied boiling water. We found that it was 212 degrees Fahrenheit, or we artificially peg it to 100 degrees Celsius. We'll save Kelvin for just a moment here. Then we'll do a human body. Approximate temperature of a human body, of course, is 99 degrees Fahrenheit. And I think that's, what, 30 something? 37 degrees Celsius. I have to admit, I would like to think more in terms of Celsius, but I still have a difficult time doing that as a red-blooded American. Okay, there's also room temperature, the temperature which is comfortable to have a room at. That's usually around 68 degrees Fahrenheit. 68 degrees Fahrenheit is probably closer to 20 degrees Celsius. Let me fact check that. Yep. And then there's freezing water. 32 degrees Fahrenheit or 0 degrees Celsius by design. The Celsius scale is considered better than the Fahrenheit one because it uses these nice whole numbers and it uses one substance, water, to define everything. I think the way that Fahrenheit evolved over time was kind of complex. Like they pegged a human body close to 100 degrees and boiling water, close to 200 degrees. So that's using two different substances, and humans are notoriously variable, right? As I discovered throughout the night. People do weird things from time to time, even crazy things. And for that reason, it's better to use a single thermometric substance like water. Water is just a little more predictable, you know? Okay, so 100 degrees Celsius for boiling water, 0 degrees Celsius for freezing water. Now, we've been measuring these temperatures longer than we even understood what temperature was. So we owe it to like Dalton and people who came up with the atomic theory of gases. These were the scientists who really went through great pains to try to understand the molecular nature of air. And they basically figured out that when they were measuring the temperature, all you need to do to measure temperature is just find something that varies with temperature and put some markings on it. For instance, put mercury in a tube and grade it out and say, I'm going to call that 0, I'm going to call that 25, and boom, you've got yourself a temperature scale. But that doesn't mean you understand what's going on microscopically at the atomic level. They had to work at great pains to try to understand that what they were measuring when they changed the temperature is they were changing the speed at which the particles traveled. That means as you cool a substance down, the speeds of the particles get slower and slower and slower, and eventually, at some point, they stop. What do we call that?
Absolute zero.
That's right. And do you remember the temperature and any temperature scale at which it occurs?
0 degrees Kelvin.
Well, that's kind of where we're going, Evelyn. So fine, you're not wrong. It turns out.
Minus 460.
That's right.
I forget which scale that's on.
So
Is that Fahrenheit?
0 is negative 460 degrees Fahrenheit, or famously, oh so famously, negative 273 degrees, negative 273 degrees Celsius. Now, Lord Kelvin, who invented the Kelvin scale, invented it after we understood that we were measuring the thermal speeds or the motions of molecules. So Kelvin's idea was, you know what? Celsius had invented a really great temperature scale. It's all based on water, and that's neat and tidy, and I like it. But I think it's kind of lame to have negative temperatures because temperature is essentially a positive quantity. When it's zero, the particles are in rest, and as you speed them up, the particles start to move. So the Kelvin temperature scale is the same as the Celsius, but it just resets the 0 point so that 0 Kelvin is absolute zero. That makes freezing water 273 Kelvin. It makes boiling water 373 Kelvin. Human bodies are around 310 Kelvin. And room temperature is around 293 Kelvin. Of course, it will be harder for us to think in terms of the Kelvin scale, and that's why this chart is nice to kind of quickly bounce back and forth in your mind. On the other hand, the surface of the sun is like 5,800 Kelvin, and that's basically like 5,000 Fahrenheit or 5,000 Celsius. So after you get to a certain height and temperature, it almost doesn't matter anymore because the numbers get so big. But for lower temperatures, closer to what we're used to, this is helpful. Okay. Now, guys, just hold on a second here. Okay. People are calling me left and right today because of some footage I got last night. So anyways, Will, nice of you to join us. Or have you been here the whole time? Sorry. I guess you were, I just didn't see you in my little window. You were here the whole time. What am I thinking? Guys, I am really out of it today. I need some more coffee. All right, we're not quite at tea break yet. Let's do a little bit on atoms and then we'll take tea break. So, Will, I apologize. I think I'm starting to hallucinate, honestly. At age 42, I cannot pull the all-nighters that I used to when I was a 20-year-old kid. So my brain is...
Hey, any possibility we can see that footage, or is that not professional?
Yeah, at the end of class, if you want to. It's pretty effing crazy. Did you see it on my it's on my Instagram, my Facebook. Honestly, if you guys want to break the fourth wall for a second, last night was just totally insane. Like the whole downtown was like a war zone, and honestly, like I'm not going to weigh into the political stuff because it's very complicated, obviously, but it certainly sucks to be on the other end of it when I had to pack a bag because I was literally concerned that someone was gonna firebomb the building, and then I'd be like half asleep, and then my building would catch on fire. And by the way, I could see City Hall. There were big burning, there were big balls of fire outside of City Hall. City Hall wasn't on fire, but there was a huge mound of something. I couldn't see what it was. So I was mostly concerned about fire. And also some of my friends run the businesses downtown, and they were struggling to reopen after. I felt bad for Karen, who runs Queen of Hearts. She's been closed now for like 2 or 3 months, and they're paying rent and they're losing money and they're stressed out, and they were about to reopen today. And now all of their windows are busted and their merchandise is stolen. So that, you know, that kind of sucks, you know. People, I also have friends that try to make arguments, you know, on both sides of the equation. And it's a worthwhile debate that I'm totally not going to fucking have with you because I'm not your political science professor or anything like that. But I am open-minded. I'm an open-minded person. I just think everyone, once you have to have a fucking bag because your house is going to catch on fire, then you're kind of like, this sucks. And when I see Karen crying in the morning and picking up her glass, that makes me sad. So it was, I'll show you the footage. It was fucking bonkers, totally bonkers.
But like that wasn't people in Providence because they've been having very civil, very productive conversations at the State House.
I saw. Well, you'll see my footage. Some of them were Rhode Islanders, you know.
Well, true, but for the most part, you could just maybe I have no idea, honestly, because they're folks I could see them. I couldn't tell where they were from, but one of my videos of looting, they're Rhode Island license plates, and they're just
running into the stores and grabbing stuff and just stuffing it into cars, and they had Rhode Island license plates. So, you know, I was an angry skate punk teen once. So I was a dummy too. I was a complete idiot, and I probably still am. So I kind of understand what it's like to have youth rage a little bit. But it was what was blowing me away is it was all really young kids. You know, like from my point of view, I'm 42, so I feel like an old man, even though I'm in the middle somewhere. But at 42, when you see 20, and some of you might be 21 years old, and you might have 21-year-old rage. So I respect that because I went through it myself. But when you see younger kids doing that stuff, I'm just like, oh man, I don't think that's the right way. Well, I don't know. This once again gets into the political debate, which I want to avoid because I don't want to offend anyone, and I don't even know if I have it all worked out in my head. But I don't think smashing the windows is good if you're in the window. It's definitely bad if you're inside the window. And I said to Jordan, I said, let's just pack a bug out bag with like a spare set of clothes, and let's make sure that if a brick comes in our window, we can get the hell out of here, especially if it catches on fire. So it was a very restless night because part of me was sitting there sipping whiskey going, oh my fucking God, you know, so, and I will show you the footage later. It's crazy. Anyways, before we get into atoms, on that note, college classrooms are a place where we can have civil discourse and discussions about these things. But maybe not too much because we want to learn some science too. Well, the nice thing about, what I love about teaching science is it's just inherently apolitical. It's about facts and observations. Yeah. It's one of the few damn things that people can agree on. Like if you got to watch that shuttle launch, I don't know if there was a person out there on Earth who didn't think that was fucking cool. If you don't think traveling to outer space is cool, I cannot relate to you on any level. It doesn't have to be your favorite thing, but you have to be at least be like, wow, what would that be like? That would be interesting. So
But then there's the flat earthers.
Yeah, or the flat earthers I might have an issue with, right? But even those guys try to launch themselves up in steam rockets, you know? I like their evil Knievel daring do. But I am so glad that I am not a political science professor because I think some of these conversations are so complicated to have, and it's hard to navigate them without sounding like a jerk. You know what I mean? Or a moron or anything like that. So anyways, it's certainly worth watching the video, and I'll show that. In fact, here, what the hell? Now, you know what? Let's save it for later. Let's take a tea break. When we come back from tea break, we'll do some atoms, okay? And we'll learn about light. And I won't subject anyone to my stupid videos unless they really, really want to see them at the end, okay? So everyone down with a little tea break for 25 minutes or so?
Yeah.
Okay. I'll see you guys in a little bit. I'll be around. Hello, everyone. I'm back. Yes, record. I hit record. How's everyone doing out there?
Alive.
Alive. Well, that's something, right? We ain't dead yet.
Yep.
Hi, Will. Nice of you to join us.
Thanks.
So I've got some more coffee, which I'm going to need. We learned about temperature. Now it's time to learn about atoms and light. Let's hope we can do it all. Jose's back. You got some nice balloons there. Was it your birthday? Happy B-Day. Woo, woo.
Thank you.
Was that today or yesterday or?
This was on that Thursday when we did the whole constellation thing, remember?
Oh, that's right. Duh. How stupid of me. Yeah, because it was your birthday when we looked up your new sign, right?
Yeah.
Sorry, that was a lot of brain cells ago, man. A lot of water sloshed between the ears since then. Okay, so let me just check the chat log to make sure. Oh, Alba, I just saw that your Trinity was vandalized as well. That's terrible. Okay, so all right, let's get to work. Let's talk about atoms and science. things that are fun to talk about. Okay, so I'm assuming, let me take a survey here. Quick show of hands. How many people have had a chemistry course? It's okay if you haven't. I just need to know what I'm working with here, so I pace it. Evelyn's had one. Sarah's had one. Laura's had one. But no, Joel. Nope. Okay, no for Shay. Joel, no.
In
Jose.
high school.
Like 100 years ago in high school.
Yeah, and
Yeah.
I had mine 100 years ago in high school as well, so I understand what you're saying there. But I mean, if I show you a picture of the Bohr model of an atom, which I'm about to do here in slide numero 7. So if we go up here to slide 7, do you guys know what we're looking at here at its most basic? I mean, what are these little pellets all called? Here's a pellet. Here's a pellet. Here's a pellet. What are those things called?
Protons, neutrons, and electrons.
That's what I want to hear. See, Shay, you've never taken a chemistry course, and you know about protons, neutrons, and electrons, and I would expect most people have. But there might be some things you don't know about these particles that I could teach you. So let's draw a picture of a Bohr model of an atom, and we'll start with a particular atom called helium, because helium is, sorry, I'm walking off camera, and I forget that you can't hear me. Helium is one of the more abundant atoms in our universe. Hey, Jordan, could I trouble you for the Windex? Actually, no, could I just trouble you for a paper towel? Because the board's getting real gicky. And when the board gets covered in gick, my markers die. Thank you. I brought some from Cece. All right. Here we go. Let's talk about the Bohr model of an atom. And today's atom will be helium. Helium is the second most abundant element in the universe, and it's a perfect starting point for your journey into the world of atoms. So I tend to draw the protons in red. Protons are positively charged particles, and helium has 2. Neutrons I draw in black, and neutrons are neutral particles also in the nucleus. So this here is a proton. This here is a neutron. And I'm going to say right now, before I get too much farther into it, that taken together, protons and neutrons are both examples of what are called nucleons. Nucleons could be either protons or neutrons. Okay, there's also electrons, and helium has 2 of them. Nice. Okay. The electrons orbit around the nucleus, kind of like a baby solar system. If I were to ask the class, what makes Earth orbit the sun, what would your answer be based on our lecture last time?
I love it so much.
No tricks. No tricks.
Gravity.
Gravity.
The force of gravity. What makes the electron orbit around the nucleus in an atom? Is it also gravity? What do you think? Sorry, Joel?
Sounds good to me.
Actually, it's would not be correct. Sorry, I did trick you. I tricked you after all, didn't I? I tricked you good. So it turns out that these particles have such small masses. We'll put it this way, Joel. I know you don't have these dry erase markers in your hands right now, but if you did, do you suspect that you'd feel a force of gravity between them?
No.
No. Because it does exist, though. They have mass and a distance in between them. We could calculate it, but I suspect it would be close to 7 times 10 to the minus 11 newtons, or something like that. Now, if I put the green marker here, or the blue one, the green marker doesn't naturally orbit it due to gravitational forces, correct? So it stands to reason that if these protons and neutrons and electrons are even less massive than these markers, there's no effing way there's enough force for gravity to keep these things in orbit. Another force is involved here. That force is electromagnetism. Let's talk about it. Oh, by the way, if you want, you can diagram the electrons here. Okay, so atoms are held by electromagnetism, and that's a new force of nature, one that you haven't studied too much. Atoms are held by the force of electromagnetism. Electromagnetism is the second fundamental force you've discussed in this class. And it has 2 rules associated. Well, first of all, in electromagnetism, electromagnetism is powered by a property called charge. In the same way that mass is part of the equation of gravity, and you could almost say that gravity is caused by mass, charge is what we call the carrier of the electromagnetic force. Charge is a carrier of the electromagnetic force. And charge works on 2 principles. The principle is that opposites attract, pluses and minuses go together, and like charges repel. In fact, if you compare the masses and the charges of protons, neutrons, and electrons, you discover something really interesting. A proton has a mass of roughly 2,000 times greater than the mass of an electron. And the charge of a proton is a positive 1. Charge is quantized into positive and negative 1s and 0s. A neutron is a big fat particle whose mass is also 2,000 times greater than the electron. Neutrons, of course, are neutral and have no charge. And thirdly, we have the little old tiny electron. The electron is 2,000 times less massive than either the proton or the neutron. Yet despite being in comparison a little tiny shaver of a particle, it has a charge equal in strength, yet opposite in value to the proton. And this makes nature very, very perverse in her design. For some reason, nature has constructed a big fat particle who is charged oppositely from a little wimpy tiny particle, at least in terms of their mass. They are symmetrical in charge, but very asymmetrical in mass. Why does nature do that? Why does she make a big fat particle the same strength as a little tiny particle? It turns out that nature is capable of reversing herself and creating what are called antimatter particles. It's possible to create a big fat negative charge called an antiproton, and it's also possible to create a positively charged electron called a positron. These bits of matter are routinely created inside of particle accelerators, and also during collisions with cosmic rays from space. In fact, during the course of this lecture, cosmic rays might pass through your body and create tiny nuclear explosions on your forehead. These are too small for you to feel or notice, but they're happening at the atomic level all the time. If they happen more frequently, you might notice, but there's not too many of them. Okay, so now we know a little bit about atoms and their subnuclear components, protons, or at least their subatomic components, protons, neutrons, and electrons. And now it's time for us to have a couple of definitions. So bear with me here as I give you some standard definitions that you're going to need to know. For atoms, I would like to define the letter A as the atomic number. The atomic number is basically the number of protons in your atom. Nothing more complicated than that. For instance, the atomic number of helium is 2 because there are 2 protons. And the significance of the atomic number is that the atomic number defines the atom itself, or what we sometimes say the element. Atom and element basically mean the same thing. Let's find a friend. Let's look up the periodic table of the elements. Bear with me as I hunt. There's a nice colorful one that I like more than others. It kind of looks like this. Let me do tools. Yeah, large resolution. All of these would be fine. I don't need to be such a nitwit about it, but there's one that I think the design of it is easier to read than others. Here. This is the one that I think is a nice one for, you know, my first periodic table when I get used to it. It's nice and colorful. They organize things pretty well. You'll notice that the atomic number is the number that you see up here in the corner. So if I can get my annotate going here, sorry. Magnesium has 25 protons, and that makes it different than chromium, 24 protons. You might think this is kind of easy or obvious, but as we start to break atoms apart, say in chemical reactions or in nuclear explosions, you will discover that it can sometimes be confusing to understand which atom you're talking about. By defining the number of protons as the atom, it helps keep your brain straight. Okay, time for another discussion. Let's talk about the letter M. The letter M is what we call the mass number. The mass number is the total number of nucleons in your atom. What are nucleons, class?
Protons plus neutrons.
That's right. So it's the total number of protons plus the total number of neutrons. Okay? And atomic number, mass number. The importance of the mass number is that the mass number defines the isotope. Any of y'all out there know what an isotope is? What's an isotope? Talk to me.
A combination of two, at least two.
Yeah, Cameron says a different number of protons than neutrons, but actually, Cameron, I'd have to correct you there. It's the same number of protons, but a different number of neutrons. But thanks for weighing in. So isotope, let's just write down the simple version, okay? Here's the simple version of isotope. It's same number of protons, but a different number of neutrons.
That's close. Close enough.
Can you all read that? I wrote that badly. Okay. Last but not least, most atoms tend to be electrically neutral. Atoms are usually 9 times, well, it depends on the circumstance, but usually they are electrically neutral. Electrically neutral means same number of protons equal to the number of electrons. So the atom that I drew for you by default, the natural business of an atom is to be neutral. You'll notice that the helium atom that we drew had equal numbers of protons and electrons, namely 2. It is possible sometimes for violence to occur, for violent actions to break out and wreak havoc among the streets. And this happens in the world of atoms as well as people. And sometimes bits get smashed and torn off of atoms. Electrons can be ripped off of them. And that's when your atom can become ionized. An ionized atom is one in which you remove, or in some perverse cases, even add electrons from the atom. This creates a fourth state of matter known as a plasma. A plasma is essentially a charged gas. It's one in which the electrons have been completely or maybe partially torn off of the atoms, and now you have a sea of charged particles bouncing around. Plasmas are more complex than normal gases because not only do they have little BBs bouncing into one another, they also have currents and magnetic fields, which make them bug out and do the matrix shuffle, and it gets a little bit complicated. We'll talk about plasmas eventually. For now, this is what you need to know about atoms. Know it and love it. Are you ready to try? Okay. So, Joel, we'll pick on you, I guess. I'm erasing. Tell me to stop now. Joel, we're going to play a game together. The game is called Let's Build an Atom. And here's how the game works. I'll tell you what the atom's all about. It's got an atomic number of 1, a mass number of 1, and it's electrically neutral. Can you tell me how to draw that atom and what it would look like?
So it'd have 1 proton, 1 neutron.
Well, almost. It has 1 proton, I'll give you that. Where'd you get the 1 neutron from? How do we define the mass number again, Joel? Wait, we just had it in our notes like 2 seconds ago, right?
Oh, wait, yeah, the number of nucleons.
The number
Protons
of
plus-
nucleons. And you yourself told me what the number of nucleons means, remember?
Protons plus neutrons.
So how many protons plus neutrons do I have?
1.
And how many
So it wouldn't
protons
have any
do I have?
neutrons.
Say that?
So it wouldn't have any neutrons.
That's my point. There are no neutrons because you've already used up your 1 nucleon. How about electrons? Any of those?
1.
Yeah, because it's electrically neutral. Do you know what the name of this atom is?
Hydrogen.
Very good. It is not just any old hydrogen atom. It's a very particular isotope of hydrogen. Does anyone remember what the name of the isotope is called? Hint, hint, Laura. Hint, hint, Shay. Who remember the names of isotopes, of course, right? Or maybe Evelyn, who's had a chemistry class. And Sarah has had a chemistry class. Maybe one of you guys know what the name of this isotope of hydrogen is called.
Deuterium?
It is not deuterium. Laura? Geez, Luis, you know, sometimes I worry that by going over this stuff, I'm going to be boring you, but this must be every bit as entertaining as it was the first time.
Blowing my mind.
Okay. It's okay. It's actually kind of obscure. The name of, because most people just call this isotope hydrogen, but hydrogen is lame. The real name of this isotope is protium. Its name is protium. By the way, I never mind when you guys don't have the answer, because that just means that you really are going to get a lot of value from my wisdom. That means I really have something to teach you. I'm not just wasting your time, okay? So this isotope is called hydrogen. Okay. Who wants to be next? Jose, do you want to give it a whack?
Let's do it.
All right, okay. Let's build another atom. We have an atomic number of 1, a mass number of 2. This atom is also electrically neutral. What do you think this puppy looks like?
Would it be a little bit bigger than the last one because it has everything just with 2?
Yeah, but I tend to not want to use the term bigger. In fact, bigger is true, Jose. You're not wrong. But when you say bigger, I'm not sure if you mean the size of the nucleus or the size of the electron radius cloud, or bigger is
only the
bit...
mass is 2. Oh, I thought you put both of them as 2.
No, the atomic number is still 1, but
Okay.
the mass number is 2. And remember, the mass number gives us what again?
Defines the isotope.
Right, but before that.
Oh, the number of nucleons.
Right. So we've got 2 nucleons. So tell me how many protons, neutrons, and electrons I need to put in this atom.
So
Why don't we-
protons
Sorry?
plus, would it be just protons and then just protons plus nucleons? I mean,
Hold on.
neutrons.
Here's how you do this. You start with the atomic number, Jose. What does the atomic number tell us?
It's 1.
And what does it in your definitions tell you?
So it defines the atom or the element.
But before that, right before that.
It's the number of protons.
So that tells me how many protons my atom has, correct?
Okay.
So how many protons do I have?
1 proton.
Good. So let's start there. Now let's deal with the mass number now that we have our 1 proton. What's the mass number tell us?
The mass gives you the number of nucleons.
Now, how many nucleons do I have so far?
2 nucleons.
Well, I'm going to have 2, but right now I'm currently only sitting on 1, right?
On 1.
I've only got
Okay.
1 poker chip on the table right now, right? So what am I going to do then? How am I going to get that other nucleon in there?
With a neutron.
Neutron.
Yes. We're going to add a neutron. Now, we have both criteria satisfied, do we not, Jose? We have 1 proton, but we have 2 nucleons. That means we win. How many electrons should I have?
So
1.
electrons.
Yeah, considering that it's neutral, that should tell you how many electrons you have. If it's neutral, electrically neutral.
Would it be 3 in total?
When you say 3, do you mean 3 electrons?
Yeah.
3 electrons would give you -3 and +1, a net charge of -2. So 3 is too many. You want balance. You want balance between your positive and negative charges, right?
Mhm.
That's what neutral means. We're not balanced because so far we have a positive particle and a neutral particle. I'm tempted to make a sort of crude analogy, but I'm worried that I already push it too far as it is here. So
Oh no, you could go way further.
I probably could. Let me try to PCify it here. Okay, it's like boys and girls. You know, an electrically neutral party is one that has equal numbers of boys and girls, right? No one. Well, all right. I'd like to say no one likes to go to a party. But see, here's where I'm going to get into some trouble. I ain't going to say shit about what kind of party anybody likes to go to. I'll go to any party as long as there's free booze, okay? And but maybe some people like to go to parties with all boys, and some people like to go to parties with all girls, and maybe some people like to go to parties with equal numbers of boys and girls. Those parties are electrically neutral, I think, as long as I didn't offend anyone there. Okay. So.
Very well put. That was very neutral of you.
Yes, I'm trying to be neutral here, okay, in the spirit of science, okay? How many electrons do you think I should have, Jose? Take a guess between 1 and 1 million, and I bet you'll guess the right number.
2.
No, it's 1. It's 1 because neutral means the charges are balanced. You need to have 1 electron for every proton. So like you're going to a party with equal numbers of boys and girls. Okay.
Oh, okay.
You see what I'm saying now? Do you get my lame ass analogy? It wasn't that great to begin with, so.
Jose.
Yeah.
X minus y equals 0.
Yes. X minus y equals 0. Okay. There we go. Now, do you want to take a shot at the? I know you haven't had a chemistry class before, so this stuff isn't going to come naturally to you like it might to others. You told me before that the atomic number defines the element. Notice that the atomic number is the same in both cases. So what would that atom be then?
It'll still be hydrogen.
It has to be because it's still got the same number of protons. The difference between this hydrogen and that hydrogen is that they are isotopes of each other. This is a particular isotope of hydrogen known as, take it away, Evelyn.
Oh, deuterium?
Deuterium, that's right. I have us try this as an example problem because deuterium and protium are perhaps the most famous 2 isotopes in the entire universe. It turns out that there's hydrogen all over our universe, including in this cup of coffee that I have here, which is mostly water plus a little bit of precious drugs. I'm going to drink it to make sure that everything's still active here. Woo! Got a little jolt, so everything seems to be working. But however, there's still quite a bit of water in this cup of coffee. And water, as you might remember, is H2O. It's an oxygen atom with 2 hydrogens stuck to it. Let's take a look at that for a second because it's quite interesting. As some of you already knew, a molecule is a combination of atoms, okay? It's a combo meal of atoms. So in water, which is one of our most basic and abundant molecules, let me skip ahead here to find water. You get 1 oxygen atom stuck to 2 hydrogens. And they are all electrically neutral for the most part. We'll talk about that. Where's the picture here? Hydrogen has usually 1 proton and 1 electron. And oxygen has 8 protons, 8 neutrons, and 8 electrons, at least in the most common isotope, oxygen 16. Hydrogen's isotope deuterium is one of the most common isotopes in nature because hydrogen is so common in nature. If you go out and travel around the universe to somewhere cool, I don't know, like say the Eagle Nebula, this is a place where I would like to be if I could go anywhere. Maybe I'd like to take a little tiptoe through the Eagle Nebula in my magical spaceship, okay? And I would sift through all of the atoms in the Eagle Nebula, counting them one by one by one, because I love the Eagle Nebula so much, I'd like to know what it's composed of. And you would discover that as you scooped up these fistfuls of gas and counted through the atoms like grains of sand, that 9 out of every 10 of those atoms was a hydrogen. So 90% of all this gas is hydrogen. And guess what the other 10% is? Helium. Most of this is just hydrogen and helium. If you want to find something more exotic, like a carbon atom or an oxygen atom, you'd have to count through thousands of atoms before you'd get to one. On the other hand, what if you just considered the hydrogen? What if you only picked up hydrogen atoms and you left the others on the ground? You'd find something interesting about your hydrogens. You'd find that not all of them were protiums. The ratio of the protiums to hydrogens is 6,000 normal protium atoms for every 1 deuterium. So there's only 1 deuterium out of every 6,000 hydrogens, and this is known as the cosmic abundance of deuterium. Believe it or not, the cosmic abundance of deuterium has been around since the beginning of the universe itself. And it's somehow responsible, or the Big Bang itself and the nuclear reactions which took place during the Big Bang are responsible for the fact that there is 1 wacky deuterium for every 6,000 hydrogens. Because the Big Bang did it, and because the Big Bang did everything, anywhere you go in nature, the ratio of deuterium to hydrogens is roughly the same. For instance, if you counted through the water molecules in my coffee cup, you would find most of them were good old-fashioned H2O molecules with protium stuck to them. But you would also discover that 1 out of every 6,000 of these H2Os wasn't actually H2O, but was HDO with a deuterium stuck to it instead. It still behaves chemically like water because it's still hydrogen, but it's a little bit heavier. By the way, if you counted through maybe 12,000 water molecules, you'd find D2O. Sounds like R2-D2 or something from Star Wars. It's D2O, and that's deuterium-laced water or heavy water. And some of that occurs naturally in the universe as well. A big goal in modern science is to measure ratios of isotopes to learn about the history of how stars, galaxies, and planets formed. And we'll be talking about that as we go forward. In any case, it's a cool and cute introduction to how isotopes work. Okay, I have some other cool things to say about atoms and molecules, but I'm gonna put them on pause for now, because before the class ends today, I'd like to get into light a little bit. Now, to get into light, I'm gonna have to talk to you guys just a wee bit about how electrons orbit inside of a atom. So let's take a look at our hydrogen atom and learn some things here. Here's a picture of a basic protium atom. 1 proton, 1 electron, 0 neutrons. And you can see that the electron is kind of orbiting around the proton on this very particular track. It's the default orbit, sometimes called the ground state. Sometimes they call this distance the Bohr radius. There's a lot of different names for it, but you guys can think of it as the default orbit, kind of like the default orbit of Earth is 1 AU. There's a real big difference between the world of atoms and the world of large things, like planets. It so happens, for instance, that Earth orbits the sun at a distance of 1 AU. But it would have been possible for Earth to orbit at any old distance you can imagine if, for instance, the finger of God pushed Earth to 1.56 AU. Well, that would be weird of the finger of God to do that, and we'd question his sanity for making such a bold move on our planet. And yet, presuming that God's allowed to do it, then nature would be allowed to do it. And that means it would be possible for Earth to orbit at 1.56 AU. However, Not even God is allowed to change the orbit of the electrons, okay? Because the orbits of electrons are fixed in stone by nature. And the electron is not allowed to orbit here, nor is it allowed to orbit here. It can only orbit there, or there, or there. It has pre-prescribed orbits. One way you can think about this is that as you get down into the tinier and tinier and tinier worlds of space, space itself becomes pixelated, or what we say is quantized. And I think you guys, you lovers of digital images, know what I'm talking about. If I go back to that Eagle Nebula picture, these clouds of gas sure do look smooth and continuous. But as you zoom in on them more and more, the round stars suddenly start to appear like a bunch of little pixels, each with a discrete color. There's a blue pixel, there's a white pixel, there's a red pixel, right? But as you zoom out, you don't notice the pixelation. The star looks smooth and round. The same is true about atoms. Atoms are kind of pixelated in the sense that they're only allowed particular orbital distances. Let's try to put that into some kind of notes or some cohesive notes we can understand. I'm going to erase my two atoms here. Okay, for a hydrogen atom, the orbits, for any atom actually, this is true not just of hydrogen, the orbits of electrons are what we call quantized. Quantized is just a fancy $10 word that means pixelated. It also means discrete. You could also call it choppy. The rungs of a ladder are quantized. You can stand on the lowest rung. You can stand on the second lowest rung, but unless you're Jesus himself and can float through the air, you cannot stand in between the lowest and the second rung. You are subject to earthly forces. And the same is true about the orbits of electrons. So let's go ahead and let's draw our hydrogen atom. We have a proton. And we have a number of possible orbits the electron can take. Oops, sorry, we're losing focus here. So the lowest orbit, ding, 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 they all have a number associated with them. The first orbit is called n equals 1. The n stands for the principal quantum number, but another way to think about n is it's the number of the orbit. And orbit 1 gets an n of equals 1. N equals 1 is called the ground state. It's the first, and it's the sort of default orbit that the electron will have when the atom is cold. The next orbit, n equals 2 orbit, is called the first excited state. That means it's the first rung on the ladder that the electron can jump to. The second orbital path is the n equals 3 orbit, or the second excited state. And there are more after this. There is a fourth orbit, and a fifth orbit, and a sixth orbit, and a seventh orbit, and an eighth orbit. In fact, you might ask me, how many orbits are there? I would say an infinite number of orbits. And then if you said, so they go on forever then, I'd say, actually, no. There is even though there's an infinite number of orbits, there's also a final orbit, which seems to make no sense. The reason why is because as you get higher and higher inside the orbit of a hydrogen atom, let's try to represent it as an energy level diagram where instead of drawing the whole orbit, we just draw a little piece of the orbit. What you can see happening here is each subsequent orbit gets a little closer to the previous one. And as you get towards the infinite number of orbits, to the 12th, the 13th, the 27th, the 52nd orbit, they all start to get so close to each other until they get to the final orbit. The final orbit occurs at an energy of 13.6 electron volts. And if you give an electron that much energy, boop, you can kick it right off of the hydrogen atom altogether. And that's when the hydrogen atom becomes ionized and forms a plasma. 13.6 eV is a famous number in atomic physics. It's known as the ionization potential of hydrogen. But I don't expect you to remember all that because that's a lot, okay? So let's talk about things that I would like you to remember for starters. I'd like you to know that there are many orbits and that I guess I will write it down. The last orbit. Okay, by the way, as the electron jumps from orbit to orbit, remember how I made potential energy earlier by lifting up my brick? This is potential energy, right? Do you remember how I called it gravitational potential energy? That's because I was fighting gravity to lift it up and down. In the case of electrons, they have electrostatic potential energy. And we tend to measure them in electron volts. So the ground state, by default, the sort of n equals 1 state, has an energy of 0 electron volts, or 0 joules. If you give the electron a kick by smashing it into another atom, you can raise it up to the second orbit if you give it exactly 10.2 electron volts. And the third orbit occurs at an energy of 12.1 electron volts. Now, I could have given them to you as distances measured in angstroms or nanometers, but F that noise. Now that we know about energy, it's way cooler to think in terms of energy. The last energy, the last orbit, occurs at an energy at infinity of 13.6 electron volts. And this is what is known as the ionization potential of hydrogen. You can think of it as, that's how much juice I got to plug into this bugger to kick its electron out of the soccer field. Now, you might be wondering why I'm telling you all this. If you kick an electron up to a high orbit, it orbits around for a while, maybe 10 to the minus 8 seconds or so. And after 10 to the minus 8 seconds, which is kind of a long time for an electron, the electron gets tired, like students get tired. And after it gets tired, the electron falls back down. And when it does so, it releases a tiny packet of light known as a photon. This process is called emission, and it looks like this. An electron oh, sorry, you guys aren't seeing my screen, are you? Sorry, there's so many buttons to keep track of here. Slide 13. Whew. The electron drops from a high orbit to a low orbit. When it does so, it releases some potential energy, and it emits a tiny packet of light called a photon. And this, my friends, is where light is born. Light is created inside the little factories of atoms as electrons drop from high orbit to low orbit. Most photons, most bits of light that you see are created in that way. Let's learn a little bit about light.
Was that how the Ghostbusters backpack worked?
Maybe. I'm trying to remember how the Ghostbusters, do they have some, it's been so long since I've seen Ghostbusters, I can't remember if they said something funny that sounded like what I said.
No, that's...
Well,
that just
Acroyd's going to have to make some money now.
Weren't they called proton packs?
Yeah, that's what they...
But I'm talking about photon packs.
Yeah, it's close.
Well,
it's just one letter.
That's kind of like saying, I'm trying to think of well, I was going to make another off-color joke, but I'm deciding to hold back today. I'm going to be on my best. The off-color jokes are going to remain off-camera. Okay. Because I was trying to think of two words.
As the Navy.
I was trying to think of two words that sound like each other. And I thought a pianist doesn't exactly resemble, and then I decided, you know what, I'm not going to go there. Okay, just because the words sound the same doesn't mean they have anything to do with each other, okay? For example, a pianist and a potato, okay? Those two things are not the same. All right, so I believe that was a within bounds joke, okay? Let's take a look at how these little packets of light work. Okay, so we have light. Technically speaking, light is an electromagnetic wave. Now, you're not going to understand all that, but that's why I have pretty pictures to bamboozle you. Let me have you write that down first on speaker view. Light is an electromagnetic wave, and it's comprised, excuse me, of little tiny packets, not proton packs, but little tiny packets called photons. Photons are to light in the same way that atoms are to matter. If someone tells you that matter is made up of atoms, most of you believe it, probably irrationally so. If I tell you that light is made of photons, I would like you to also irrationally believe me in this. Proving that is a little bit of work. And here's a little cartoon model of how they behave. Oops. I'll share my screen. Light, this is a model of light taken from a physics textbook. It has two components to it. One part is an electric field, which is associated with static charges, like when you rub a balloon on your head or pull your socks out of the dryer. The other is a magnetic field, which is related to magnets. The electric field and the magnetic field are both part of the electromagnetic force. And photons have a field, a magnetic field and an electric field, and they kind of oscillate through space. Here's a more sophisticated picture in which the electric field is shown as a bunch of green arrows and the magnetic field is shown as a bunch of blue arrows. Now, for those of you with a teensy bit of math training, this is an example of what is known as a vector field. A vector field will unfortunately be over many of your pay grades, but a vector field is kind of interesting because it's kind of like all the points in the room have a value. Like if you go to your house, it's not always the same temperature. One corner of the room might be 66.5 degrees and the other corner of the room might be 66.7 degrees. That's called a scalar field because it's just numbers. But in a vector field, you have numbers plus directions in all locations. It's wild. Mathematics is wild. Get into it. Okay, so in any case, light's pretty confusing. It's an electromagnetic whatchamahoozit, and it travels through space at the speed of light, and it's got some properties, okay? So light is created inside of atoms. When electrons drop from high to low orbit. And like waves of all types, light has three properties that we're going to be studying here today. And the three main properties of photons are what's called the wavelength, the frequency, and the energy of light. The wavelength gets a symbol called lambda. It looks like an X that's missing an arm. That's the Greek letter lambda, and it stands for the wavelength of light. Frequency, we use a lowercase curvy f for, and energy gets a capital E. I'll explain each of these things. The three properties of light, wavelength, frequency, and energy, are related to each other by two famous formulas that I'm trying to squeeze in before the end of our lecture today. Oh, fuck. We're supposed to do the inverse square law. Rubbing my head, rubbing my temples, trying to figure this out. All right, let me just get these formulas up and then I'll go from there. All right, the first formula, which I'm going to call Formula 1, tells us that the speed of light is equal to the wavelength times the frequency, where the speed of light, c, is a new constant of nature. It's the speed that light travels in a vacuum, and it's always the same value. 3 times 10 to the 8 meters per second. The second formula gives us the energy of a photon. It tells us the energy of a photon is a number called Planck's constant multiplied by its frequency. Just bear with me here. Planck's constant is a tiny little number that shows up anytime you deal with the world of atoms or quantum mechanics. Planck's constant, little h, has a value of 7 times 10 to the minus 34 joules times seconds. Now, if you want to know what Planck's constant is, well, you're in for a haunted hayride. It's kind of complicated. But particles like protons, neutrons, and electrons, they have a quantum property called spin, which is kind of like the spin of my little moon ball here. And the spins of them are not smooth and continuous like a record player, but the spins are jerky, and they happen in discrete increments, like jerk, 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 jerk. Almost like you were twisting a socket wrench or something. Right, Shay? You know about twisting socket wrenches, right?
Indeed. What I was gonna ask about that though is every time a certain amount of time, or is it just, you know, like, oh, this one's a nanosecond, that is there any
I wouldn't put it in terms of time. I'd put it in terms of spin. Weirdly, Shay, a joule times a second has the same units as angular momentum. So what Planck's constant is it's the smallest amount of spin that a little particle can have. So think of it as the particles spin in increments of Planck's constant. The lowest spin it could have would be to spin, I don't know, 1 Planck's constant at a time. And then they could spin it twice Planck's constant or 3 times that. So you might think of it as how many twists of a socket wrench. Imagine your socket wrench, you can twist it, you know, a quarter turn or a half turn before you have to go back up. Planck's constant is telling you the increments of the turns and what the smallest possible turn is.
okay.
In the same way that a socket wrench clicks, right? Click, click, click,
Right.
click, click.
Right.
These are the clicks, you know. That's a somewhat crappy analogy, but I'm going with it. The third formula that you're going to need to know is a combination of Formula 1 and 2, and it's kind of nice. Let's add some stuff to our notes before I erase. Do you guys see wavelength? Let's talk about the units. The units of wavelength are meters. The units of frequency are cycles per second, or hertz. And the units of energy are joules, or you could use electron volts. I should point out that 1 hertz, a frequency of 1 hertz, is equivalent to 1 cycle per second, but cycle is like a dummy unit. So weirdly, hertz are the same as 1 over seconds, or inverted time. Now, these are real actual things. Let me show you your light wave. And right now, I could be imagining some students being like, what the F in hell are you talking about? Okay, fair. Let's imagine this is a little wave of light. Let's demonstrate wavelength, frequency, and energy if we can. The wavelength of the photon is the distance from crest to crest. So the red arrow that I just drew there is approximately equal to your wavelength. It's the distance from crest to crest. It's also the distance from trough to trough or from node to second repeating node. It's basically the length over which the pattern of the wave repeats. Okay, what about the frequency? The frequency is the number of cycles per second. Let's try to measure the number of cycles per second by putting up a barrier and counting the number of waves that pass through with time. In fact, I have a stopwatch here, or we could try to use our minds too. Let's see how my mind compares to my stopwatch. Okay, so I'm gonna draw a line as this thing moves. Can I? Oh, I can't do that. So let's erase that. And let's put my mouse here, and we'll start counting when the crest goes by, okay? Oops, sorry, my mouse. Okay, that's not gonna work. I'll start counting when it goes by this crest. Actually, I know. We'll put a star here. Cool. All right. It's a shitty gold star, but whatever, gold star. Here we go, ready? 1001, 1002, 1003, 1004. Am I good? No, I was off by a second. 5 seconds. I counted 4. I wanted to see if I could count as good as a stopwatch. I discovered I cannot. This wave has a frequency of 1 cycle every 5 seconds. What is 1 divided by 5, class?
0.2.
That means the frequency of this wave is 0.2 hertz. So there's 0.2 cycles coming by each second, or 5 cycles, 1 cycle in 5 seconds, right? Okay, cool. The third formula, which relates these two things together, is a formula that looks like this. The energy of a photon is Planck's constant times the speed of light divided by the wavelength. This is somewhat unnecessary because we already had formulas 1 and 2, but this is just the energy of a photon. And I like it because I tend to think in terms of wavelength. Most optical astronomers think in terms of wavelength rather than energy. I am now ready to introduce you guys to something called, well, first of all, let me let you finish what I wrote. I need to stop lecture, by the way, it's 3:02, so this has to be my last point. I know, Laura, me too. I'm not being as engaging because I'm very, very sleepy. I'd like to end off by introducing you to something called the periodic table of the, the electromagnetic spectrum. That shows you where I'm at. The electromagnetic spectrum is the totality of all the different types of light that exist in nature. The only thing that makes one type of light different than another type of light is the wavelength, which is the distance from crest to crest. Your eyeballs are sensitive to a pitifully narrow range of electromagnetic radiation, which go from 400 nanometers, which you call purple, to a wavelength of 700 nanometers, which you call red. But there are many other different types of light out there in nature. There are gamma rays, which come from nuclear explosions, and X-rays, which also come from nuclear explosions, and ultraviolet photons, which give you sunburns at the beach, and infrared photons, which help you turn on the TV and help warm you up if you're standing in front of a radiant heater, like a toaster. And then there's radio waves, which allow you to communicate with your cell phones. We are going to be studying all these types of light in detail, and I'll cover more of that on Thursday. For now, I'm going to have to stop. Let's talk about lab today. We didn't learn the formula that we're going to study in lab, which is shitty, but we can do it. The lab is kind of short and it sometimes works badly. Let's give it a quick try and see if it works out okay. And if I can shorten this lab, I'm going to, because I had an extraordinary night and a lack of sleep. I'm being a big baby and I'm starting to get really loopy on you guys. I did consider canceling lab, but which I'm sure everyone would have been fine with. But we're here anyways. Let's just do a little teeny something, and then I'll give you your 10 points. Is that okay? Let's do something halfway in between nothing and something, okay? So let me keep recording, and let me move over here. Fudge, I didn't really figure this out here. Hold on, guys. I've got quite an elaborate lab set up here today, which you can all see. You can see I've got an optical bench out and some crazy stuff. Let me figure out how am I going to do this. I forgot that the computer needs to go in front, not behind this thing. So I'm going to pull it in. Put the computer back here. Okay. Do you guys have the printout that I gave you? Anyone? Laura's got it. Do we need a second before we get started? Or are we kind of good to go? Let me get my mouse. All right.
It's the light bulb one?
Yeah, it's called the inverse square law.
Okay.
Even though we haven't covered, my goal was to cover the inverse square law, and if I had had another half an hour, I probably would have gotten to it, but I did not have that half an hour. So I'm just gonna go with this, all right? We can still do the lab. The idea is to measure the intensity of light in a unit called lux as a function of its distance from a light source, which I have set up. Oh, fuck, hold on. Those are my hard drives. God damn it all. Ah. I got to be careful how I move this thing around, because if those hard drives go kaputs, then this whole class is kaputs. So we can't have that happen. Okay, sorry. Let's see here. I might want to get out my cell phone. I was trying to twist it over so you could see my light source. I'm going to turn that on for you guys. I have a feeling this is going to be an extremely irritating lab. Hold on. It'd be cool if I had a switch. I guess. I could have a switch. Hold on. Hold on, guys. I'm having a brilliant idea. I'm going to rig up the lamp. With this switch here, which is a little power strip. And that way, when I flip the switch, oh, it doesn't even really flip that well. Oh, figures. Huh. I get the world's, okay. You know what? I'll just plug it and unplug it. That's how it's going to be. It just be like that sometimes. Okay. Here I have a little light detector. It's funny. It kind of looks like a hot dog. The reason why it looks like a hot dog is there's a sensor here called the little CCD chip. That little square chip that you can see is a light detector or a light sensor. But when I held it in without the styrofoam, it kind of flopped over all floppy-like, and I needed to kind of support it. So thus we invented the styrofoam hot dog, okay? And that's going to go on this holder. And our goal is to try to measure the intensity of light as a function of distance. Um, hold on. Let me get a pad for my mouse here, because it doesn't like the glass countertop. And I'm going to try to go into phone mode so that I can tour you around the setup here. Let me also hit print on my lab, which I forgot to do amid the chaos. I have a copy of it up and ready to go here. We're going to need these 3 pages. So I'm going to hit print. And all right, cool. Meanwhile, back at the ranch, I'm going to stop the share, and I'm going to try to send you guys to my phone so you can check out the setup. All right, guys, I'm going to warn you that my phone has been going nuts today because of the photos that I posted of the looting. Every 20 seconds, like news organization. Well, during the course of this lab, I've been getting contacted by news organizations, the local business owners, people, skate punk teens that I know are yelling at me. So my phone's going to be popping the fuck off today, okay? And it's ridiculous, but I have to share this with you. So just be prepared for that, okay? My phone's kind of going nuts. Thank you. Oh, you got me a marker? I forgot that I'm going to have to share my phone with them while all this nonsense is going on. It's going to be cray. Hold on, guys. I'm trying to get my, here we go, screen mirroring up. All right, so just beware. You're going to see a lot of nutty text coming up during the course of this lab. Okay, here's my setup. I have a source of light, and rather than just have the light bulb shine, do you guys see how I put some tin foil over it and I poked a little hole in it? This is going to make an artificial star, a point source. And I've got a lab bench set up here, and I've got this kind of sausage hot dog light detector, and then I've got a screen that's going to measure the intensity in lux. You guys might actually want to use the Microsoft Word version where I changed some of the columns, but here's what we're going to be doing. Let me do this in pen. Why the hell not? I usually don't, but let's put our name and then AS1020, okay? We're not going to be doing a 60-watt light bulb. We will only be doing a 100-watt light bulb. And we're not going to be measuring the intensities in foot candles. We're going to be measuring the intensity of light in a unit called lux. Now, the purpose of this lab is to prove something called the inverse square law for light. The intensity of a light source does not stay constant as you get farther away from it. And you guys already know that. If you look at a light bulb on the other side of the room, it becomes, well, dimmer to your eyes anyways. The intensity becomes less. And the intensity is the luminosity or the wattage of a light bulb divided by 4 pi times the distance squared. And that means that the way that light falls off through space is somewhat related to the way that gravity works. You'll remember that the force of gravity was inversely proportional to the square of the distance. And we made a whole big hullabaloo out of that. It turns out that the intensity of a light source also drops as 1 over the distance squared. These are what are called inverse square laws in physics. And inverse square laws appear all the time and are an important part of nature. For instance, electromagnetism is an inverse square law. But I digress. An inverse square law means that if you double the distance, the intensity should fall off by 1 over 2 squared, or the brightness or intensity should be 1/4 as much. If you triple your distance, your intensity should be 1/9. What if you quadruple your distance? Kids?
One,
If I quadruple my
1/16th.
distance, huh?
1/16th.
Next stop, rocket science. We're ready to go here. The inverse square law means that if you make a plot, chin camera here. If you make a plot of the intensity of a light source as a function of distance, and you plot the light meter at 10, 20, 30, 40, 50 centimeters, the intensity should fall off like the graph of 1 over x squared. And I bet you guys had to take a crappy little math class at some point where you found that the graph of 1 over x squared kind of looks like that, right? Ever have to do that in algebra class? Some of you have actually tried to avoid algebra.
Yeah. I did it last semester with quantitative business analysis.
Was that fun?
I enjoy math, so.
Oh, that's cool. I enjoy math too, although it's not always so. Anyways, we're going to see if we can reproduce this plot. This is the graph of 1 over x squared, which is the same thing as 1 over d squared. It doesn't really matter what the variable is. The intensity should drop off exponentially with a nod to the exponent. Okay, so let's just kind of get into it. Who cares if you understand it or what? Guys, I cannot just simply measure the intensity of light as a function of distance from the light source. Not only is my light meter going to be capturing photons from this little artificial star, but look, there's light coming in from the windows. There's light bouncing off my face, my black shirt. There's photons that are going to leak in the side, and it's pointless to try to get them all. So what we're going to do is we're going to switch the light bulb on, and we'll take a reading, which is the source plus the background photons. Then we'll switch the light off. And when we switch the light off, we will be measuring the background in lux. And then by subtracting on minus off, we will just get the intensity or the source as a function of distance. Since I'm going to be doing it for you anyways, why don't we just kind of start and see how it works? Because honestly, I'm too tired to explain any more than that. And you're probably too tired to listen to any more than that. Let's just do it, and maybe you'll understand something as we go, okay? So, God, one thing that I realized I did wrong is I foolishly put my light source at 100 centimeters, which is quite lame because it would have been nicer if I put it at 0 centimeters, right? But I don't feel like resetting it up right now, so we're going to kind of go backwards. Let me kind of adjust my light source. I want to make sure that my pinhole is as close to 100 as possible. I also want to make sure it's somewhat down the axis. Okay. Now, can you guys do me a favor? On this sheet that you have, can we change our values? We're not going to go 30, 40, 50, 60. We're going to go 10, 20, 30, 40, 50, 60, 70, 80, 90. All right.
Are our columns different than yours? Because the printout says source and background for the first column. I don't know if that's going to matter.
Did you print out the docx one?
Maybe.
I forgot that I think I only uploaded the docx. I have to make these adjustments every time, and they're annoying. So I think I tried to make them for you. Does yours? That's going to confuse the shit out of you, though, isn't it? And that's fair. Hold on.
We could just change for it to say source and background for the second. And
No, I like it to say source plus background first. I like the way yours looks more than mine. Can I just download exactly what you have, and then we can avoid this crapola?
Yeah.
I had to log into Blackboard because it logged me out.
Of course it did.
By the way, A couple of you who I graded last night, should I take a peek and see who did naughty and nice for their grades so far before we forget? A couple of you I know were in class and did not submit something. That tells me that you may not realize that Blackboard fucked up your submission.
Uh-oh. Yeah.
I think it was your
Yeah.
class. Hold on, let me just go up here. If everyone's comfortable with seeing who's who, which I don't think is a huge deal. Cameron, I'm missing your period of the ISS. Alba, I'm missing your period of the ISS. Catherine, you're not here in class today, but you're gonna watch the video later. And you're missing the period of the ISS, okay? Okay, so how about the homeworks? Cameron and Alba, I know you're on the chat log there. You're chatting. Are you chatting me? I'm afraid to stop the phone share.
I will say yes.
Thank you. So, okay, Alba, please submit your period of the ISS, okay? Okay, she got me. Thanks. Let's scroll over here and see if anyone's missing any homeworks. Because most of you are here for it. Catherine, when you watch later, I still don't have your homework 3. Cameron, I do not have your homework 3. And Alba, I don't have your homework 3. So Cameron and Alba, you got to submit your stuff or I'm going to come and I'm going to hunt you down and shout you out. Okay? All right, now that we've put that unpleasantness behind us, let's download your version of the lab. Oh, what the fudge. Oops. Apparently I don't know my own damn password.
Into a
Huh?
cat on the bed.
There's a cat? What's this about cats?
Yeah. Well,
Hold on. Whoever's talking is glitching the shit out. Was that? I'm going to download the one that you guys have, which I should have done in the first damn place.
Hey, Brandon, I actually have the one, this is Shay, I have the one that you have because I still have the lab book.
Oh, fudge je ne stick. Okay.
Well, I'll print out if that, I mean, yeah, if everyone else has that, I'll just pull, what the hell, right?
Yeah, it's only a second of printing. Sorry, guys. There's always bullshit when we do these labs. They're hard to do online. You know, at the office there at CC, I've got a lab tech and I've got all this stuff. And I still have my lab tech for spiritual support and for technical support by phone, but it's not the same. She's a wonderful woman and talented, but I miss Renee in my life every day. Okay. Is this what your paper looks like, guys? Can you see my phone?
I
Oh,
see the old one.
are we not screen sharing right now?
There's a picture of the old phone, but it doesn't look like it's live.
Oh, yeah, I think it froze out. Oh, let me stop this shit.
taking a nap.
Huh? Oh, you could see it?
It's sleeping.
It's sleeping, yeah.
Nope, not anymore.
Just like I'm gonna be. Hold on, I'm trying to share it again. Oh, this is my big fear. My big fear was that I would lose it. Oh. Fortune pisses on me. Okay.
What about your iPad?
Yeah, I might try that. The thing about the iPad is it's kind of unwieldy. What's cute and what works about the phone is you can kind of dink, 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 put it around. You know what I mean? So, hold on, I'm doing a system reboot. Plus, how am I going to show you guys all the looting? Oh, when you were out, you missed my problem about candy bars today. It was pretty funny. Hold on, guys. Let's try this one more time. Share screen. Here we go.
Tell her how many kilogram squats you have to do.
42,000 kilogram squats to burn off a candy bar. She said yes. I'll be starting that right after class, guys. Right after class, maybe after a sandwich. Okay. You know what happens is on the phone, sometimes it works and sometimes it doesn't, and there's no fucking rhyme or reason whatsoever. It says, oh, if you don't see because I have to go to my share screen mode. You know, I might have to use the iPad out of desperation. Sometimes it shows up and sometimes it doesn't. That's why once you see me get it, I'm really loath to stop. Oh, this is terrible. It's absolutely terrible. Ouch. Ouch, that lamp is hot. Okay. Hold on, kids. Hey, maybe I could use your phone. Yeah. Do you feel okay with that? Yeah, that's fine. I don't get notifications. Oh, okay. Well, you're smarter than me. Hey, I'm gonna see if I can use Jordan's phone. Hold on a second. I just need to activate the screen sharing. Maybe the newer phones will work better. Just have low battery, but, I can plug it in over here. Yeah. Can I see that? You just log into Zoom? No, well, no, it's not like that. It's you have to use a screen sharing technique. Oh yeah, I think I can. That's easy. I just thought maybe because your phone is newer, it might work more reliably than this old piece of shite. Yeah, go into the settings. No. It's having the same issue. I'm sorry, guys. Can you just bear with me? I'm having technical glitches, and I'm deeply sorry. I'm gonna have to restart again. So once I get my phone sharing, I should never ever stop for this reason. So far, I've always managed to make it work, but it has done this to me before. All right, so we're going to go with the new paper, right? All right, I'm trying this again. Yes. Fucking A. All right. Here I am. I'm at my light sensor, and we're going to take the values for 10 centimeters. Everyone understand what we're doing here?
Yep.
Good. And
Yes,
even
sir.
if you don't, just pretend you do, and I won't notice, okay? All right. Do you see how I had to do that? Let me go into my settings and display. Auto lock. Oh God, I've never been more popular with the glue sniffers. Okay, here we go. Thanks. All right, guys, here's my light sensor. My light sensor is currently set to 90 centimeters. I have no idea if this is going to work because I had to dismantle it and remantle it. And we're reading approximately, wow, it's jumping around quite a bit. Do you guys see how it's oscillating like that?
Yeah.
I think that might be the alternating current. When I do this at CC, I use a DC generator to keep the current steady, but it's oscillating 60 cycle current through that light bulb. And I suspect that's making micro fluctuations in the intensity of the light. I cannot think of why else it would be varying by so many lux. We're gonna have to round off and go with, wow, now it's up to 450. Did you guys see it drop down to 420 a moment ago?
Yeah.
Am I in the right setting here? I'm between, I should be between 0 and 600. Let's try that, see if I get a steadier signal. Ooh, no, I was in the right one. I was in the right range. They have a range of intensities. I'm currently in the 0 to 600 range. Whoa. I wonder if my phone is contributing to it because it's a radio emitter or something. Or it's, no, that doesn't make any sense. Okay, so 458, or let's go with 455. That's our source plus background. We're just trying this out to see if it works. And now what I'm going to do is I'm going to kill the lamp and we're going to take a background reading.
That's at 10.
That's at 10. So source plus background, 455 lux. Our background looks like it's about 224. We're just going to take it and we're going to move. We're not going to overanalyze it. And now we have to subtract to get the difference. 455 minus 224 is 231 lux. All right, let's keep moving here. Next up, I'm going to slide my sensor to 20 centimeters, more or less. And first, we're going to flick the lights on. Oh, you bastard. You dirty bastard. Ah. Okay. All right, lights are on. Sensor's reading. What do you think? Wow, it's jumping all over the goddamn place really fast. No, that's particle radiation, not electromagnetic radiation. It does this in the lab room too. I've never quite figured it out. Wow, I just watched it drop by 30 lux. That's kind of, maybe I need to move to the side and keep a very steady position. The amount of light that I reflect off of my shirt will affect this. I don't know about 30 lux, but maybe. I'm going with 285 because it's in the middle. I suspect I need a DC generator to keep that light steadier. Okay, now we're going to do the background. Unplug. What do you think? I can't believe it's oscillating like that. I'm not sure what that's about. The noise, it's the noise floor. The noise is at least at the 30 lux level. It's crazy. Let's go with 175. And we'll subtract. 285 minus 175. This is.
I feel so bad for you.
I feel bad for me too. All right, I'm one step away from abandoning this. Hold on a second. I have gotten this to work good in the lab, but something's not right. Do you guys see how we're 231 divided by, sorry, do you see how it's 231 over 110?
Yeah.
That's half. It's not called the inverse law, it's the inverse square law. If I double my distance from 10 centimeters to 20 centimeters, I should be dropping by a factor of a quarter.
Oh.
That tells me, and do you see how wildly different the backgrounds are? Look at this, by the way. Look. The background is now 115.
You think it has to do with your computer light?
No, that wouldn't be enough.
Oh.
Like, look, if I think about the amount of lux that it is if I pointed at a sunny window, right? If I take this little bugger and I'm just inside of a room, the ambient light in the room is hundreds of lux. The computer light can't be contributing as much as sunlight. Let me go back one more time. Let me go back to 10 centimeters. I'm going to try this one more time and then I'm abandoning ship, okay? And
Yeah.
you might this might just be a failed lab and we might have to deal with it. But let me give it one more college try, okay? And I do mean college try. There we go. Okay. Currently the light off. Our background here reads 123 or 124, 125. You'll notice that the background we had before was 224. Perhaps that was too high. This is why you should use pencil and not pen. That would mean our source well, let me get my source reading again as well. Wow. That is do you guys see how it seems to be oscillating?
Yeah, big time.
It's not just going up or down or fluctuating randomly. It's going down to like 370, and then it's jumping back up to 420 and then back down again. That tells me there's some process it's got to be electronic in origin. I can't think of what else it would be. I don't think the light is changing by 50 lux in this background room. Do you see what I mean? I'm getting some bleed in through the shades there, but it's staying pretty constant. I don't expect to see such a, wow, now it's up to 450 again. At school, I have DC generators to help with this. I'm not sure why. I guess I could have set this sensor up wrong, but I don't think so. Maybe I can change the duration of the samples. Oh no. They take a sample 20 times per second.
Huh.
That's pretty impressive, right?
Yeah.
All right. Suppose I do 455 minus 125. All right. You know what, guys? On a normal day, I would beast this thing, but something is going wrong and I don't know what it is. And rather than make you sit here and watch me troubleshoot it, especially when I'm tired and not firing on 100% cylinders, I think I may just have to just abandon this lab. All right. This lab has always given me trouble, but it's given me an extra lot of trouble today. I know that kind of sucks. On the other hand, I tried it. I don't see any point being a dead horse. My other labs don't have the same problem that this one does. The sensor is very sensitive. I suspect, I'm very curious about what it is. That's the thing that's, the hardest thing for me is not walking away from the lab, is not knowing what's causing it. And my suspicions are that there's something to do with the alternating current passing back and forth through the lamp, that it's causing a fluctuation in intensity. Either that,
I'm the same exact way. I'm mad because you can't figure it out because I'm a friggin' mechanic, right? The one thing that I would do, and this, I don't know, I just shoot from the hip. That 20 times per second, I'd switch it to 1 time per second if you can, and see if that makes a difference.
Yeah, and you're, as a troubleshooter, that's in your biz, then
well,
you're
especially with alternating current, you know what I mean? So if you only do it 1 time a second rather than 20, it might not be so haywire, or it might be more haywire. I don't know.
Yeah.
It's worth a try.
If it's super haywire, do 100 times per second.
Yeah.
Well, what we want is for it to be steady so we can get dependable results.
Yeah.
And Shay, if you notice, it's kind of not fluctuating quite as much, is it?
Might be too sensitive because it alternating, you know, I know what you're saying. Like you hooked up to DC before, so it's more steady.
Oh no, here we go. Here we go, look.
Shitting up again.
You're still sharing your laptop camera, not the phone camera.
Oh, so, yeah. Thanks. I apologize. Let me try it. Let's see if my phone camera even works.
Still screwed up, huh? Well, it's worth a shot.
For a moment, it looked really steady, so I thought you would solve the problem. But then I watched it go from 470 to 440 in an instant. Let's just check on it for a second.
Yeah.
So right now, it does the same patterns. Woo, there we go.
Just with bigger jumps. It goes bigger. Huh.
No, the jumps were way crazier before. I think that did, I don't know what duration 10 seconds mean. That's one thing I'm not sure about. Samples to be collected. Durations. I'm not sure about the duration. Well, we only got this sensor in a year or two ago, so I'm still kind of figuring it out. I know what the rate means, and I know what the interval means. I don't know what the duration means. Let's change that to 1 second too. Let's make everything 1.
Hey.
Seems a little steadier at first, right? But look.
Yeah, there it goes.
All right. I'm gonna have to put some thought into this. Honestly, I think part of it too is just because I didn't get much sleep last night. Can we chalk this up to a professor sick day?
Yes.
Okay. Do you want to see the pictures of what I saw last night? I don't know if that's of interest to you or not, but
I do. If you can hang on for another five or 10 minutes, yeah.
Yeah. I mean, it's I've never seen anything like it, so it's pretty wild.
Yeah.
Brendan, did you notice somebody started following you with the name Satan in it?
With a what?
Their name on Instagram was something Satan. I noticed that pop up on your phone.
Oh,
that's cool.
boy.
That's great. I'm not afraid of Satan. Honestly, half my friends are Satanists, and so you know, I wouldn't be surprised. I keep a lot of weird friends, guys. Hold on, let's see if I can share this with you. I didn't notice Satan following me, but
Satan himself is following you.
Wouldn't be surprised if the devil himself was coming after me. Hold on a second here. Let's see if I can. Oh, it's doing the thing again. Hold on. I should have just kept it up there. It'll work one time. Every piece of electronics in my life is going crazy. I think it is Satan. I think Satan's possessed all of the people and the electronics. This is like a big poltergeist that's going on downtown.
Either that or the moon, right?
Yeah.
Well, as an astronomer, I'm not allowed to say that. I don't know if I believe it's the moon.
Right.
all of the loose electrons are jumping ship.
Yeah, maybe it's all them loose electrons that are messing everything up. Yeah. I'm starting to feel like a loose electron myself. You know what they call? They call loose electrons the valence electrons. The final electron in an atom is called the valence electron. And when you conduct a current of electricity, it's that electron which is shared amongst all the atoms. So I'm starting to feel like a valence electron myself. I'm sort of dangling by a thread here. All right, let's try this again. So share screen. Okay, here we go. All right, hopefully they're. Oh, there we go. All right, so let's see what we got here. There was some nuttiness last night. Oh, I don't know. That's what I was watching last night. Those are people running out of the store with bags of fucking goods.
Jordan and I are up here in the window watching the whole thing go down. It's fucking insane. They're destroying everything. Oh, now they're smashing the tree out the house. Hold on. I'll let you know. There's no cover.
That was outside my window last night.
Wow.
Yeah, do you understand why I'm a little frazzled today?
Yeah.
That was going on all last night, right outside my window. We were half concerned that we were going to get, look at these people jumping in the windows. It was like a war zone, guys. It was like a war zone. Part of City Hall was on fire. It was insane. I've never seen anything like this in my life. And you think that's bad? Check. I was willing. This is another one. And I know the girl who owns the shop. She's real sweet and a hard worker. She was scheduled to reopen today. She's been suffering through the COVID pandemic. And that poor woman has to come to.
Did you get that?
Oh my God.
I can't see it, but I can hear it. Oh my God. What's happening right now? The water.
Oh, fuck. Oh, fuck. You getting this?
Wait, Brendan,
Yeah.
did you notice that the people that broke the windows are wearing NASA shirts?
Yeah, both
I
of
did
them.
notice that. I thought about that. They're like robber astronauts.
Robber astronauts.
I did notice they were wearing NASA
Holy
shirts, and I
shit. Are you
thought that
seeing
was
this,
pretty
Dan?
weird.
Yeah.
So yeah, guys, that's sort of, imagine that was my entire night last night. Like I couldn't sleep because I wasn't sure if the next brick wasn't coming through my window or if they were going to set the building on fire. Like when they were doing it at the mall, that was one thing. But once it was all these like small businesses and once it was my house, then it got fucking scary. You know what I mean?
Shit.
Is everything going to be boarded up tonight? Because they're probably going to do it again, right?
It's already,
Jeez.
honestly, that was like kind of the most amazing thing of the community thing. What I wanted to, I didn't post it on social media because people are popping off, especially in my friend group. Everyone's real touchy about politics. And what I kind of felt like saying, just kind of to a smaller group of people was, you know, the real community action, like peaceful protesting, voting, and all the people that came out the next day to help clean up, they're already boarded up. First thing in the morning when I was like trying to get to sleep so I could teach this lecture coherently today, people were volunteering out in the street, like sweeping up glass, boarding up things. It was actually kind of, it was beautiful. You know, like all these people came together to try to like make it better, which is what I think community activism should be about, you know, making better things, not worse things. But people are pissed off, and rightfully so. Some fucked up shit's gone down. So I'm not insensitive to the other arguments. I don't think personally, I don't think breaking a store window gets anybody justice, but
No.
maybe
Yeah.
it definitely raises the bar for the conversation. You know, we're talking about it now because that was crazy. So there is a certain logic to that. I don't know if I love it, but
But Brendan, the one thing I noticed, and it may have been the light, but most of those people that were on the streets last night were white.
Yeah. me
a lot of
too.
them were, but there were people of all types. Like I tried to take a look at that because I was wondering, oh, is it just going to be a bunch of suburban kids coming in to bash the shit up? But it from my ground level perspective, because I walked around in it. I left the apartment and I went up to the mall just to kind of see what was going on and trying to stay out of the tear gas canisters. It was a pretty, I wouldn't say I could say it was all white kids or all black kids or anything like that. It was a pretty good ethnic mix, but they were younger than me. I felt old there. Like they all seemed like they were in their early 20s or late teens. And that's what was kind of wild to me, is that it was all like, in my experience downtown, I've always gotten robbed by some scary looking stocky plumber dudes or something. You know what I mean? Like I'm not used to getting robbed by kids.
Yeah,
no,
right.
I wasn't personally robbed, so I'm okay. But it was so many young people. So either the young people are really pissed off, which is definitely true, but they're also like, sometimes young people can be a little callous too, you know? Like they don't always, I can only say this for myself being a young person, you're a little numb and you don't always think through the consequences. You're not thinking of the fact that there's a woman named Karen Beebe who's been stressed out about whether she could keep her store and had to come to work today and pick up the glass and pick up the pieces of her life. And she's not a person who is privileged. I know that woman. She worked at bars and restaurants like the rest of my friends and saved up money and busted her ass for that store. So she wasn't the corporate man. She also had, you know, she had signs in her window in support of the protests, but that I believe are sincere, knowing her personally. So she wasn't just some cigar chomping monopoly man. You know what I mean? So I think young people sometimes forget that they're like, they don't think through some of the longer consequences. So I think it wasn't I don't think it was a color issue personally. I think, or I couldn't say it. There were definitely a lot of white kids on the street and there was black folks, there was all folks, but it was young people. It was young people. And that's what was kind of like, holy cow to me. I couldn't believe that all these kids were fucking assholes. You know what I mean? Like, I mean, and they might have a legitimate reason to be angry that society, I'm kind of sitting pretty, right? I got a nice cushy job as a teacher and they might be seeing their economy collapse and feel like, well, fuck it, anarchy is better than the shit that the older generations did to me. I don't personally feel like I did it to them, but maybe somehow I did, I don't know, you know, but it's a really complicated argument, which is why I tried to stay out of it. I mean, it's hard not to talk about it because when you see that happening, you say, holy shit, how do we get to this point, you know? But the young people, that was the thing that really got me. So we have to talk to our youngsters and you know, I don't know. It would have been nice if they came and helped pick up the next day.
Yeah.
Maybe then I would have understood it, you know, I don't know. But I think they're just making off with the skateboards or something. Anyways, I'll leave it there because I'm definitely not an authority to speak on these issues. I don't think I have it all figured out myself, but it was a wild night downtown and I sure hope that's the last of it. And I promise I will get more sleep before our next lecture if the madness allows it. Okay, guys?
Good luck.
Yeah.
Yeah, and stay safe.
Well,
Truly.
you guys too. And remember, if you do go out to a protest, wear your mask and make sure science. We should think about science in this class. And in keeping your mask on, it's probably doesn't help a ton, but it helps a little bit. And every little bit helps. One thing I was thinking about with all those protesters is, holy shit, you're all going to be increasing the reinfection rates if you're shoulder to shoulder, you know? So I think the protests are important. I might go to a peaceful one myself. I'm down to peacefully protest, but some of those people were like, no, well, I guess they had masks on, but it was just, I don't know. There's a lot for me to process, guys. I haven't thought my way through it. Anyways, why don't you guys have a good day? I'll stop the recording now.